They are exiles of cosmic violence, stellar phantoms ejected at unimaginable speeds, tearing through the galaxy like bullets fired from the heart of stellar catastrophes. They travel so fast, not even the gravity of an entire galaxy can hold them. These are the runaway pulsars, neutron stars born in chaos and hurled into the darkness with no path back. But where did they come from? Why were they flung away? And what secrets do they carry, traveling as rogue witnesses to cataclysmic events that remain unseen? The mystery of runaway pulsars is not just a tale of motion, it is a tale of trauma, violence, and the silent aftermath of cosmic war. It is a story written in the language of supernovae, magnetism, and speed, and today, we're going to explore everything we know, and everything we don't, about these speeding anomalies of the universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand runaway pulsars, we must first understand what a pulsar really is. A pulsar is a type of neutron star, an ultra-dense remnant left behind after a massive star explodes in a supernova. But not all neutron stars are pulsars. Pulsars are unique because they emit beams of electromagnetic radiation from their magnetic poles, and if these beams sweep past Earth like the light from a cosmic lighthouse, we detect them as periodic pulses. These pulses are incredibly regular, some down to milliseconds, making pulsars some of the most precise clocks in the universe. But some of them don't sit quietly in space. Some are moving, racing, through the galaxy at speeds exceeding 1,000,000 kilometers per hour. The fastest ever observed, Pulsar J0002 plus 6216, is traveling at 1,130 kilometers per second. At that speed, it could cross from New York to Los Angeles in just 3 seconds. These aren't gentle drifts, they are galactic ejections. The term, runaway, is no exaggeration. These pulsars are literal escapees, flung so fast that they are on trajectories that will take them entirely out of the Milky Way. Think about that. The Milky Way is over 100,000 light-years wide, and yet these tiny, city-sized remnants of dead stars are moving fast enough to eventually break free from its gravitational grip. How could such a small object move so quickly? The key lies in the dramatic, almost theatrical, nature of their origin stories. Most runaway pulsars are thought to be ejected during the supernova explosions that created them. When a massive star goes supernova, the explosion is not always symmetrical. If one side of the blast is slightly more forceful than the other, it can create a powerful recoil effect, launching the leftover core, the newborn neutron star, in the opposite direction at incredible speed. This asymmetry could be caused by uneven shockwaves, instabilities in the core collapse process, or even interactions with magnetic fields during the final death throes of the star. The resulting motion is so violent that it gives birth to one of the fastest moving objects in the known cosmos. But asymmetric supernova explosions are not the only way a pulsar can become a runaway. In binary star systems, where two stars orbit each other in a cosmic dance, if one of the stars goes supernova, the sudden loss of mass can disrupt the gravitational balance. The explosion can eject the remaining core in one direction, and the surviving companion star in another, turning both into runaways. Some runaway stars we observe today may actually be the counterparts of runaway pulsars, each flung from the same cataclysm, now separated by thousands of light years, each moving independently through the void. Pulsars are already exotic enough, objects so dense that a teaspoon of their material would weigh billions of tons, spinning at mind-boggling rates, generating magnetic fields trillions of times stronger than Earth's. But when one is moving, its mystery compounds. How does its velocity affect its magnetic field? What happens to the trail it leaves behind? Some runaway pulsars drag tails of shocked particles behind them, cosmic contrails glowing in X-rays shaped by the interstellar gas they plow through. These glowing tails can stretch for light years, making the pulsars look like comets screaming through the galaxy. In fact, Pulsar J0002 plus 6216, the fastest known pulsar, has a tail of shocked gas 13 light-years long, longer than the distance from Earth to the nearest star, Proxima Centauri. That pulsar is not only notable for its speed but also for its origin. It was likely ejected from a supernova remnant called CTB-1, a fading, shell-like bubble of gas over 10,000 light-years from Earth. Based on its speed and current distance from the center of that remnant, astronomers estimate it was ejected around 10,000 years ago. And it has been racing ever since, completely unaffected by anything in its path. The void of interstellar space offers little resistance. There is no friction, no drag. Once moving, these pulsars are destined to continue on, unbound and unstoppable. Studying runaway pulsars does more than just satisfy curiosity. They are probes, clues to the hidden dynamics of supernovae. By tracing their paths backward, astronomers can identify the sites of ancient stellar explosions. By analyzing their speeds, we can test models of core collapse physics. By studying their motion, we can learn about the gravitational structure of the Milky Way. These stars don't just tell us about themselves, they tell us about the galaxy they came from and the explosive violence that birthed them. But even with the data we have, many questions remain unanswered. Why do some supernovae produce runaway pulsars and others don't? Why do some pulsars travel faster than others by such wide margins? Are there even faster ones we haven't found yet, perhaps already outside the Milky Way, no longer broadcasting their pulses in our direction? Could there be entire populations of runaway pulsars we've missed simply because their beams don't align with Earth? These are not idle questions. They are active areas of research, with implications that stretch across astrophysics, cosmology, and gravitational theory. Interestingly, some theories propose that the kicks responsible for runaway pulsars might be linked to more exotic physics. There are ideas involving neutrino emissions, ghostly particles that escape from collapsing cores in enormous quantities. If more neutrinos are emitted in one direction than another, it could create a thrust that pushes the pulsar away. But how would that asymmetry arise? Could it be linked to conditions during core collapse, or even to unknown aspects of particle physics? This brings runaway pulsars into the realm of quantum uncertainty, where the tiniest imbalances at the subatomic level can launch a star at nearly 1% the speed of light. Others suggest the involvement of strong magnetic fields twisting and exploding like coiled springs in the heart of collapsing stars, releasing angular momentum and magnetic energy asymmetrically. Still others look to turbulent convection currents deep inside the imploding core as the chaotic mechanism for uneven thrust. And none of these ideas are confirmed. That's the beauty and the curse of studying runaway pulsars. We can see them. We can measure their speed. We can trace their paths. But the moment of their birth remains hidden in the clouded remnants of exploded stars. Sometimes, runaway pulsars are found far from any visible supernova remnant. Does that mean the remnant has faded beyond detectability? Or were they born in ways we don't yet understand? Could some of these pulsars have been ejected by forces other than supernovae? Some astronomers have even speculated about interactions with black holes, gravitational slingshots that could theoretically fling neutron stars into intergalactic space. While there's no direct evidence for such scenarios yet, the mere plausibility opens up thrilling questions about gravitational interactions in densely populated regions like galactic centers. And speaking of the galactic center, what happens when runaway pulsars originate from there? Could some be launched by interactions with the supermassive black hole at the core of the Milky Way, Sagittarius, say? Could stellar collisions or three-body interactions near the galactic core create such high velocities that a pulsar is flung away, forever leaving the spiral arms of its home galaxy behind? These are not just possibilities. They are part of the ongoing investigations into high-velocity stellar objects. Some of the fastest objects we observe today, both stars and pulsars, do indeed trace their trajectories back to the center of the galaxy. What mechanisms exist there that could explain such violent expulsions? As these galactic fugitives blaze their way through the cosmos, they don't just carry the legacy of the explosions that birthed them, they also reshape the space they travel through. Runaway pulsars create bow shocks, arcing waves of heated gas and magnetic fields that curve like the prow of a ship slicing through water. These bow shocks, observable in X-ray, radio, and optical wavelengths, reveal the violent interaction between a pulsar's magnetic wind and the interstellar medium. They act like fingerprints at a cosmic crime scene, showing us not just where the pulsar is going, but hinting at how fast it's moving and how it's distorting the fabric of its environment. Imagine this: a neutron star the size of a city, moving faster than a bullet, dragging a colossal magnetic field and spewing out high-energy particles into space. It creates a shockwave that lights up the interstellar gas like a wake of cosmic fire. And these aren't theoretical constructs, we have observed them. The Guitar Nebula, for example, is a visually haunting bow shock left by a pulsar racing through the galaxy. It's shaped eerily like a guitar, its glowing trail carved into the gas of the Milky Way as the star moves at hundreds of kilometers per second. It is an art piece left behind by a stellar projectile. And here's where it becomes even more fascinating. These bow shocks not only tell us about the pulsar, they also act like interstellar probes, revealing the density, composition, and behavior of the interstellar medium itself. In many ways, runaway pulsars are natural spacecraft, cosmic test particles launched by nature to map out the properties of galactic space. They give us insight into things we otherwise could never measure so precisely, such as the distribution of interstellar matter or the structure of magnetic fields in the galaxy. But there's an even more thrilling angle to consider. Some of these runaway pulsars are headed into intergalactic space. If they're moving fast enough, and many are, they will eventually escape the gravitational grasp of the Milky Way altogether. Once outside, they will become lone travelers in the void between galaxies, drifting across trillions of kilometers of nearly perfect emptiness, likely never to encounter another star again. What happens to a pulsar in such an isolated state? Could it become a beacon in the dark between galaxies? Could we detect these wanderers from Earth, using sensitive telescopes tuned to their periodic pulses? Some astronomers think we might already have done so, mistaking them for odd radio bursts, unexplained flashes, or even confusing them with fast radio bursts, FRBs, another ongoing cosmic mystery. Runaway pulsars might also help us answer questions about dark matter. Since their velocities are so extreme, their paths through the galaxy are influenced subtly but persistently by gravity. If we can precisely measure their trajectories over time, any unexplained deviations might hint at gravitational influences we can't see, possibly indicating the presence of dark matter clumps or substructures. This would make runaway pulsars not only tools for studying star death, but instruments for probing the invisible scaffolding of the universe itself. Then there's the question of how many runaway pulsars exist. We've found only a few dozen high-velocity neutron stars, but astronomers estimate there should be hundreds of thousands of neutron stars in our galaxy. Many of them, potentially millions, might be runaway pulsars we just haven't detected yet, either because their beams don't sweep past Earth, or because they've already traveled too far and grown too faint to detect. That opens up the possibility of a vast unseen population of stellar outcasts, drifting through the halo of the galaxy, or even roaming the intergalactic void, like orphans of celestial disasters long past. In recent years, new telescopes and observation strategies have begun to uncover more of these elusive objects. Instruments like the Fermi Gamma Ray Space Telescope and the Very Large Array have picked up clues of rapidly moving pulsars, not just in radio, but in gamma-ray and X-ray wavelengths as well. Some of these objects move so fast and so far from their origin points that astronomers have had to reverse engineer their trajectories, using simulations to estimate the time and location of their explosive births. These simulations sometimes reveal multiple plausible birthplaces, but occasionally they trace back precisely to known supernova remnants, tightening the case for a violent, asymmetric kick at the moment of stellar death. Even more intriguingly, the phenomenon of runaway pulsars opens the door to asking what happens when neutron stars collide, not in mergers, but in near misses or interactions in dense stellar environments. Could gravitational interactions in stellar nurseries or globular clusters eject neutron stars in much the same way gravitational slingshots work for spacecraft around planets? Could close encounters between multiple massive stars early in their lives set the stage for high-velocity ejections after death? If so, then runaway pulsars might also hold clues to the dynamics of the early Milky Way, the crowded, turbulent environments where many massive stars were born. Runaway pulsars might even challenge what we understand about galactic escape velocity. Typically, We think of the Milky Way's escape velocity as around 550 km per second near the Sun's orbit, but this number changes depending on the direction, altitude, and location within the galactic halo. Pulsars moving above this speed, like Pulsar J0002 plus 6216, have confirmed that compact remnants can exceed this limit. They are nature's own hypervelocity stars, but far denser and more extreme. Their presence confirms that supernova explosions can create objects that not only survive a massive detonation, but are flung so hard that they escape everything that once bound them: mass, gravity, magnetism, even their own stellar neighborhood. The thought that these objects, born in destruction, become uncatchable ghosts in the dark is profoundly poetic. And that poetry hides within it a mystery still unresolved. Why do some supernovae impart such enormous kicks, while others result in relatively stationary neutron stars? Could it be differences in core composition? Neutrino asymmetry? The influence of strong magnetic fields or rotation? Or is there some quantum chaos at play, a fundamental unpredictability in how the core collapses, like a roll of cosmic dice determining the fate of a neutron star? In trying to answer that, scientists have begun developing advanced simulations of supernova events that include effects like convection, turbulence, rotation, magnetic flux, and even quantum particle transport. These models attempt to reproduce the violent, complex environment of a core-collapsed supernova, and in some cases, they do show asymmetric explosions leading to high-velocity kicks. But none of them have fully explained the highest speeds we observe. There's still a gap, a missing mechanism or an unknown variable, something we've yet to uncover that would close the mystery of what propels a neutron star to become a runaway. There are even more speculative theories, some suggesting that exotic forms of matter inside neutron stars, like quark-gluon plasma or hyperons, could play a role. If the internal structure of a neutron star varies dramatically under different conditions, the resulting energy distribution in a collapse could be very lopsided, delivering the kind of asymmetric thrust we observe in runaway pulsars. These ideas push the boundaries of physics, straddling the frontier between what is observed and what is theoretically possible. And yet, while scientists model, simulate, and debate, the pulsars keep moving. Silent. Relentless. Driven by ancient violence, they pass unseen across the sky, many too distant or faint to detect, many no longer aligned with Earth, many forever beyond our reach. But for those we can see, we gather their light. We measure their speed. We trace their trails through space. And we listen to their steady, ticking pulses, like the heartbeat of a ghost that refuses to die, traveling ever outward into the unknown. Some of these ghostly heartbeats are so regular, so precise, that they rival the most accurate atomic clocks humans have ever built. A runaway pulsar, spinning hundreds of times per second, maintains a rhythmic signal with such fidelity that even across thousands of light years, we can detect slight irregularities, glitches, timing noise, or sudden changes in frequency. But when a pulsar is on the move, those changes are not just from internal physics. They also include Doppler shifts from its motion through space. If it's speeding toward us, the pulses arrive slightly faster. If it's racing away, they stretch. And that very stretching becomes a tool, not just to confirm motion, but to study it in exquisite detail. We can watch a runaway pulsar's journey unfold over decades. Slight changes in pulse arrival time across years allow scientists to calculate not only the pulsar's current velocity, but also its acceleration and trajectory. This kind of motion tracking turns a single object into a test case for physics, astrometry, and galactic dynamics. It allows us to ask, how is the galactic gravitational field structured at large scales? Where does the dark matter lie? How do magnetic fields evolve in the galaxy's outer regions? These questions, once considered abstract, now find partial answers in the data whispered to us by runaway pulsars. And when the pulses suddenly glitch, spinning faster for a moment, like a gear clicking into a new notch, it reveals secrets of the neutron star's interior. These glitches may be caused by the interaction between a superfluid core and the rigid crust, which momentarily snaps and transfers angular momentum. It's like an earthquake inside a star that's moving at hundreds of kilometers per second, a star so dense that one sugar cube of its matter outweighs Mount Everest. Imagine a quake on something so dense it crushes atoms, still pulsing and spinning as it races away into the void. But for all that they tell us, runaway pulsars also conceal much. Most neutron stars, including the runaway variety, are detected through radio astronomy. Their beams of emission need to point toward Earth for us to see them at all. And that's the problem. The pulsar's beam is narrow. If it's not sweeping across our planet, the pulsar is effectively invisible. These undetectable pulsars, known as radio-quiet or orphan neutron stars, might vastly outnumber those we've catalogued. If the distribution of beam angles is random, it's possible that for every detected runaway pulsar, there are hundreds, even thousands, slipping through space unseen. To find these hidden travelers, astronomers have begun using other tools, especially X-ray and gamma-ray telescopes, which can sometimes pick up emissions from pulsar winds or bow shocks, even when the beam itself misses us. Some missions, like NASA's Chandra X-ray Observatory, have revealed X-ray trails stretching behind neutron stars like galactic comets. Others, like Fermi, have detected gamma-ray pulsars whose energies dwarf those of their radio counterparts. These multi-wavelength observations are the future of runaway pulsar research, piecing together a hidden population from the shadows of electromagnetic radiation. And then there are the ultra-fast pulsars, those moving at velocities that suggest something even stranger at work. PSRB 1508 plus 55, for example, moves at over 1,100 km per second, suggesting an unusually strong supernova kick. But even more mystifying is the possibility that some of these objects are not simply moving fast, they are spinning faster than should be possible. Millisecond pulsars, rotating hundreds of times per second, are believed to have been recycled in binary systems, spun up by accreting matter from a companion star. But some high-velocity pulsars challenge this narrative. How could they have gained such speed and maintained such rapid spin if they were ejected so violently? This paradox hints at a complex pre-supernova history. Perhaps these pulsars were once part of compact binaries, pairs of neutron stars or neutron star, white dwarf systems. When one exploded, it hurled the companion out like a slingshot. That companion, if it had already been spun up by prior accretion, would retain both its spin and its new velocity. This scenario could explain why some runaway pulsars rotate rapidly even after being ejected. But these systems are rare, and the exact conditions required are not yet fully understood. Again, the runaway pulsars taunt us, offering partial answers while concealing deeper truths. In rare cases, pulsars might even be part of a double runaway scenario. Imagine this: two massive stars orbit each other in a tight binary. One explodes and forms a pulsar. The system survives for a time, the pulsar spinning, accreting, emitting. Then the second star goes supernova. Depending on the mass loss and direction of the blast, the system might be destroyed, with both stars flung in different directions. In some simulations, both stars, now neutron stars, are accelerated to enormous velocities, becoming twin runaway pulsars, heading off in opposite directions. If we ever detect such a pair, years or light centuries apart but clearly linked by trajectory and age, it would be a cosmic smoking gun, revealing the aftermath of binary destruction at galactic scale. Of course, in many cases, the companion is not another neutron star, but a black hole or an ordinary star. If the explosion disrupts the binary, the remaining companion may also become a runaway star. In fact, some of the fastest-moving massive stars we've detected, called OB runaways, might be survivors of such events. In this context, runaway pulsars are not isolated phenomena. They are part of a broader ecosystem of stellar ejections, neutron stars, white dwarfs, massive stars, and perhaps even black holes, all flung out from violent events. The Milky Way might be constantly launching stellar shrapnel from its own internal detonations, scattering compact remnants across interstellar and intergalactic space. And some of that shrapnel may come from places we rarely think about, like globular clusters. These dense star clusters, often found in the galactic halo, are packed with hundreds of thousands of stars in tight configurations. Within them, close encounters between stars are far more likely than in the galactic disk. If a neutron star formed in such a dense environment, it could be ejected by gravitational interactions long before any supernova kick occurs. In fact, studies suggest that many runaway pulsars may originate from such environments, not flung by explosions, but by three-body gravitational dynamics. These, dynamically ejected, pulsars represent an entirely different class of runaway, their speed not imparted by death, but by the chaotic dance of gravity among too many neighbors. And that leads to another mystery: what happens when a runaway pulsar encounters other objects in space? While space is vast and mostly empty, over millions of years, even a fast-moving pulsar may cross paths with molecular clouds, gas-rich regions, or even the remnants of other supernovae. These encounters can trigger shockwaves, alter local magnetic fields, or even seed new regions of star formation. A runaway pulsar is not just a passive traveler, it can be an agent of change, disturbing the equilibrium of space as it passes through. The gravitational influence of a neutron star, though small over long distances, can nudge smaller objects like comets or rogue asteroids. Some theorists have even suggested that runaway pulsars might play a subtle role in triggering star birth or disrupting protoplanetary disks. What if, in rare cases, a runaway pulsar passes close to a dormant black hole? What if their paths bring them into gravitational resonance, creating detectable gravitational waves? While the probability is low, the stakes are high. Such an encounter, if observed, could provide insights into the interaction between extreme gravitational objects, data that could be folded into theories of general relativity, neutron star structure, and quantum gravity. Runaway pulsars may be the hidden messengers of high-energy astrophysics, drifting through the dark until they collide, figuratively or literally, with the right target. And even beyond our galaxy, there's the possibility that similar processes are occurring. Other galaxies, especially starburst galaxies and irregular dwarfs with high rates of star formation, likely produce their own populations of runaway pulsars. Some of those, ejected at high enough speeds, may even drift into intergalactic space, eventually intersecting with our own observational reach. Perhaps some of the high-energy signals we detect from deep space, mysterious point sources of gamma rays or X-rays, are not from exotic alien objects, but simply the afterglow of distant runaway pulsars, flung from galaxies we can barely resolve. If this idea proves true, it would mean that runaway pulsars are not just messengers of events within our own galaxy, but relics of cosmic violence on an intergalactic scale, travelers that have endured the forces of stellar death, escaped the grip of their home galaxies, and continued across the abyssal void between galactic systems. In such a context, each runaway pulsar becomes a living fossil of stellar evolution, a record etched into spinning iron and magnetic fields, slowly traversing distances so vast that human comprehension falters. And what about the future of these interstellar vagabonds? The journey of a runaway pulsar doesn't end just because it exits the Milky Way. Their lifespans as pulsars, the visible, pulsing phase, may last tens of millions of years, gradually spinning down until they become undetectable. But they never really die. As neutron stars, they remain intact for billions of years. Long after their light has faded, long after our species is gone, they will continue their path outward, becoming cold, dark cinders, ghosts of stellar cataclysms, moving ever farther into the emptiness between galaxies. And there, in that silence, they may someday form part of the dark cosmic infrastructure that shapes the universe's large-scale structure, moving masses of dead matter, quietly warping the fabric of space-time with their persistent gravity. But it's not only their fate that fascinates us, it's their potential. Some astrophysicists have proposed that these high-velocity objects might be harnessed as tools for deep space physics. If, in the far future, humanity becomes a spacefaring civilization with the ability to travel or observe across interstellar distances, runaway pulsars could become waypoints or lighthouses, stable timing sources, gravitational probes, and cosmic beacons guiding ships or probes through the dark. They might even serve as precise navigation markers, much like GPS satellites do for Earthbound travelers. Indeed, the incredible timing regularity of many pulsars has already led NASA to experiment with using them for autonomous navigation of spacecraft, a technique known as XNAV, X-ray navigation. And runaway pulsars, moving through otherwise empty space, could become ideal tools for such applications, undisturbed, isolated, and incredibly consistent. Still, many mysteries remain. We don't yet understand how the most extreme of these objects attain such phenomenal speeds. Some velocities exceed even what current models predict is possible from asymmetric supernovae. Are we missing something fundamental in the explosion mechanism? Is there an unknown force, process, or particle involved? Some theories suggest neutrino-driven asymmetries, others point to intense magnetic field reconnection, and still others invoke asymmetric mass ejection or fallback onto the neutron star. None have yet provided a complete and consistent explanation across all observed runaway pulsar data. The truth may be a combination of all of them, or something else entirely, still undiscovered. And then there are theories that verge on the speculative, the edges of scientific imagination. Some have proposed that certain runaway pulsars could, under the right conditions, collapse further into black holes, not because of added mass, but due to phase transitions within their exotic interiors. These so-called strange stars, composed not of neutrons but of deconfined quark matter, might be metastable, eventually succumbing to a collapse triggered by some unknown catalyst. If such an event were to occur in a fast-moving neutron star, it could release a sudden burst of gravitational waves or gamma rays detectable across vast distances. In this way, runaway pulsars might be ticking time bombs, harboring extreme physics within, waiting for a final transformation. Moreover, the paths of runaway pulsars may tell us about the long-term evolution of our galaxy itself. As they stream away from the disk, often into the galactic halo, they become data points for mapping the structure of the Milky Way's outermost regions. Their accelerations, decelerations, and deviations help map gravitational anomalies and test models of galactic mass distribution. Their distribution, how many, how fast, in which directions, reveals where star formation was most intense, where binaries were most common, and where supernovae occurred in greatest numbers. In a way, each runaway pulsar is a tracer particle in a vast astrophysical fluid, letting us reconstruct the invisible currents of stellar formation, death, and migration that have shaped the Milky Way over billions of years. What's more, they can even challenge our understanding of stellar evolution. Some runaway pulsars appear to have formed in environments where supernovae shouldn't have happened at all, regions with low metallicity, or isolated from known star-forming clusters. This raises questions about our models. Did these stars migrate before exploding? Or is there a class of massive stars that can go supernova under unexpected conditions? Alternatively, were they ejected by dynamic interactions far earlier than assumed, carrying with them secrets of a birthplace long since vanished or unrecognizable? Our tools for answering these questions are rapidly evolving. Next-generation telescopes like the Square Kilometre Array, SKA, the Vera C. Rubin Observatory, and future X-ray observatories will vastly increase our ability to detect faint pulsars, track their movements, and even detect previously hidden ones through their secondary effects. We may find entire populations of previously invisible runaway neutron stars, allowing us to develop a much more complete picture of their numbers, origins, and contributions to galactic dynamics. With enough data, statistical analysis could reveal patterns, preferred directions, correlations with galactic structure, or even relationships to ancient bursts of star formation or galactic mergers. Then there's the role runaway pulsars may play in the broader story of cosmic entropy. These compact stars, once vibrant and energetic, carry the thermodynamic imprint of their violent origins. As they cool, slow, and fade into the deep galactic night, they become components of the universe's growing cold graveyard, the vast background of inert, slowly decaying matter left after energy has done its work. But in their motion, they retain a relic of the energetic processes that once shaped galaxies. Their kinetic energy, carried into the infinite future, becomes one of the last remaining motions in a universe fated, perhaps, to end in stillness. And beyond the physics lies something deeper, the symbolic resonance of these stars. They are survivors. They are the result of destruction, yet they endure. Their journeys are solitary, yet they connect us to vast structures and hidden forces. They speak to the idea that even from cataclysm, something coherent and lasting can emerge, something that moves forward, that tells a story, that echoes across space and time. When we detect a runaway pulsar, we are hearing the echo of a star's death cry, stretched across light years, transformed into a rhythmic pulse by the crushing grip of gravity and the residual spin of a collapsed core. We are catching a message that has traveled across the void, a relic of chaos, now orderly, a signal that bridges violence and silence. And that message doesn't just tell us about the pulsar. It tells us about the galaxy, about stars, about life and death, about how motion, even at its most violent, is part of a greater symmetry. And so, with each discovery, with each wandering star found far from where it was born, we glimpse more than just an astrophysical oddity. We glimpse a truth about the universe, that nothing ever truly stands still, and that even in exile, even alone, even cold, something once powerful can still move forward, unseen, unforgotten, and unbound. And perhaps it is that metaphor that draws us to these objects so deeply, not just as scientists, but as storytellers. In a universe so vast and indifferent, a single object that carries the memory of its birth and the inertia of its trauma becomes more than just a compact remnant of a supernova. It becomes a cosmic pilgrim, etched into the very fabric of time. The runaway pulsar is a paradox, the aftermath of collapse, yet the embodiment of momentum, the relic of destruction, yet the signal of survival. Their stories, hidden in data, gradually unfold as astronomers piece together their origin, journey, and destiny. Through proper motion measurements, parallax data, and Doppler shifts, we reconstruct not only where they are now, but where they came from and when they left. These reconstructions have allowed scientists to track some runaway pulsars backward in time, pinpointing supernova remnants that may be their origin sites. One such example is the guitar pulsar, named for the guitar-shaped bow shock it creates as it plows through the interstellar medium. By analyzing its trajectory, astronomers traced it back to the Cygnus OB3 association, a dense star-forming region. It's a haunting realization. This lonely neutron star, now hurtling through the void, was once part of a vibrant stellar nursery, surrounded by light, heat, and companionship. But now it races alone. Its bow shock, a glowing arc of gas compressed by its speed, leaves behind a visible trail, like a signature scrawled across the interstellar canvas. It is as if the runaway pulsar refuses to go quietly, instead marking its presence with kinetic fire and magnetic turbulence. In some cases, these bow shocks have even been detected in infrared, revealing the interaction between pulsar winds and cold molecular clouds. The shockwave can ionize the gas, heat it, and even carve out tunnels through denser regions. The trail, though ghostly, is a real force, reminiscent of the way a boat disturbs water as it passes through. Other pulsars are far more elusive, traveling through regions of low density where no visible shock can form, leaving behind no visible trace. These are the true silent wanderers, escaping not only their birthplace but even detection itself. Yet even in these cases, careful measurements over decades, or subtle distortions in the background radiation, may one day reveal their passage. The motion of runaway pulsars has another surprising implication. Some of them may escape entirely from the gravitational grasp of the Milky Way. While the escape velocity from our galaxy depends on the location and distribution of dark matter, it is estimated to be around 500 to 600 kilometers per second near the Sun. Several pulsars have been clocked with velocities exceeding 1,000 kilometers per second. These hypervelocity pulsars are rare, but their existence suggests a future where they drift indefinitely through intergalactic space, never to return, forever exiled from the galaxy that birthed them. We usually think of galaxies as closed systems, collections of stars and gas held tightly by gravity, but the presence of these runaway objects reminds us that galaxies leak. Not just gas, not just dark matter, but stars, remnants, even black holes may be ejected into the great void. Some may end up in the galactic halo, or in the thin filamentary tendrils that connect galaxy clusters. Others may fall into the intergalactic medium, contributing to the diffuse matter that bridges cosmic structures. And some, moving quickly and quietly, may continue until the end of time, undisturbed, unobserved, and unbound. The implications of this for cosmology are vast. If enough of these high-velocity remnants exist, they may contribute to the missing mass problem. While they wouldn't account for all of the dark matter, a population of invisible neutron stars and black holes streaming through intergalactic space could make up a small, yet significant, fraction of the baryonic mass budget. The existence of these objects might even help explain subtle discrepancies in cosmic background measurements or gravitational lensing data. Runaway pulsars also provide a unique opportunity to test general relativity. As they travel at relativistic speeds and pass through different gravitational potentials, their timing and trajectories become natural experiments in curved spacetime. By comparing their observed behavior to precise theoretical models, scientists can look for deviations, tiny inconsistencies that might point to new physics. Could their acceleration be slightly off from predictions? Could their light pulses be delayed more than expected? These discrepancies, if real, could become the next cracks in our understanding of fundamental physics. Some researchers have speculated that runaway pulsars might even be responsible for mysterious cosmic phenomena. One hypothesis is that fast radio bursts, FRBs, brief, ultra-powerful flashes of radio energy, could be caused by interactions between high-velocity neutron stars and dense interstellar clouds, or by magnetic reconnection events triggered during flight. While no conclusive evidence links the two yet, the extreme energy and mobility of runaway pulsars make them intriguing candidates for exotic astrophysical signals. Another layer of mystery involves the magnetic field strength of these objects. Some runaway pulsars are magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. A magnetar traveling at high velocity through space becomes a moving generator, interacting with galactic magnetic fields, sweeping up charged particles, and possibly igniting plasma instabilities in its wake. These interactions could create faint radio tails or even trigger synchrotron radiation observable from great distances. The combination of motion and magnetism in these stars is a cocktail of incredible astrophysical potential. Think of it, a hypermagnetic object, more dense than atomic nuclei, spinning rapidly, and plowing through space faster than most spacecraft can dream of moving. It's not fiction, it's a real object in our galaxy. It's no wonder that even the most seasoned astrophysicists find runaway pulsars endlessly fascinating. They are like spinning knives thrown into the cosmos, slicing silently through the interstellar medium. Runaway pulsars force us to think differently about motion, energy, and isolation. They show us that not all movement in the universe is slow and stately. Sometimes, motion is violent and unpredictable. Sometimes it is forced upon a star not by its own will, but by the death of another. And yet, from that chaos emerges something remarkable, an object that holds onto its coherence, its timing, its pulse. An object that, despite being cast out from the only home it ever knew, continues to shine. We are still learning what these stars can teach us. We are still cataloging their numbers, tracing their paths, and decoding their signals. New surveys will surely reveal more. And maybe, just maybe, among them will be a pulsar with a trajectory so unique, so fast, so distant, that it rewrites everything we thought we knew. Maybe it will lead us to a forgotten supernova, or a strange quark core, or the edges of our galaxy's gravitational influence, or perhaps to the beginning of something else entirely. Whatever they reveal, one thing is certain: runaway pulsars are among the most haunting, awe-inspiring, and enigmatic travelers in the universe. And as long as we have the tools to listen, the patience to wait, and the imagination to wonder, their journey will continue to unfold, pulse by pulse, light year by light year, across the eternal dark. To truly appreciate the enigma of runaway pulsars, we must delve deeper into the physics that governs their birth and subsequent acceleration. A pulsar is born in the fiery crucible of a supernova, an explosive death throe of a massive star at least 8 times the mass of our Sun. When the star exhausts its nuclear fuel, its core collapses under gravity to a city-sized neutron star, a compact object packing more mass than the Sun into a sphere barely 20 kilometers across. This collapse releases a staggering amount of energy, ejecting the star's outer layers into space at thousands of kilometers per second, and lighting up the cosmos with a brilliant supernova explosion. But what causes some of these newborn neutron stars to be flung away at speeds so extraordinary that they escape their home galaxies? The leading theory involves asymmetries in the supernova explosion itself. If the explosion is perfectly symmetrical, the resulting neutron star should remain nearly stationary relative to its birthplace. However, real supernovae are messy affairs, and small imbalances in the explosion's force can impart a substantial kick to the neutron star. This kick can be likened to the recoil felt by a gun when a bullet is fired, only on a cosmic scale. Scientists have long sought to understand the precise mechanisms behind these kicks. Some propose that anisotropic neutrino emissions, where more neutrinos are emitted in one direction than another, could provide enough thrust to accelerate the neutron star. Neutrinos are nearly massless, ghostly particles produced in vast quantities during core collapse. If their emission is uneven due to magnetic fields or convection currents inside the collapsing star, it could produce a net force pushing the neutron star away. Others suggest that hydrodynamic instabilities in the exploding star's core cause directional ejection of matter, physically propelling the neutron star opposite to the bulk of the expelled gas. Beyond these mechanisms, the complex interplay of rotation, magnetic fields, and stellar structure likely influences the velocity and direction of the pulsar's kick. Some runaway pulsars spin at incredible rates, hundreds of rotations per second, hinting that their birth conditions involved rapid rotation coupled with intense magnetic fields. These magnetic fields, twisting and contorting as the star collapses, could channel energy unevenly and contribute to the asymmetric explosion. The magnitude of these kicks is astonishing. While most stars in the Milky Way orbit the galactic center at a leisurely few hundred kilometers per second, some pulsars rocket through space at speeds exceeding 1,500 kilometers per second. To put this into perspective, the fastest spacecraft built by humans, such as the Parker Solar Probe, travel at a mere fraction of that speed relative to the Sun. These pulsars are true speed demons, cosmic projectiles hurled into the void with an energy rivaling that of the most powerful explosions known. As these pulsars race through the galaxy, their interaction with the interstellar medium creates unique observational phenomena. The pulsar's strong magnetic field accelerates charged particles to relativistic speeds, generating beams of electromagnetic radiation observable as pulsations when aligned with Earth. Moreover, the collision of the pulsar's wind, a stream of charged particles emitted from its magnetic poles, with surrounding gas produces a bow shock visible in radio, X-ray, and optical wavelengths. These bow shocks, often shaped like cometary tails, serve as cosmic signposts marking the pulsar's trajectory and speed. The discovery and study of runaway pulsars have been greatly aided by advancements in radio astronomy. Pulsars were first detected in 1967 as sources of periodic radio signals, and today, sensitive radio telescopes survey the sky to catalog and track thousands of these objects. Their precise timing, down to microseconds, allows astronomers to measure their motion across the sky with remarkable accuracy. Combining these measurements with models of galactic dynamics helps reconstruct their origin and predict their future paths. Some runaway pulsars have even been linked to known supernova remnants, allowing for the identification of their birth sites and the study of supernova explosion mechanics. For instance, the pulsar known as PSR B1508+55 was measured moving at nearly 1,100 km per second, and its trajectory traced back to a supernova remnant in the Milky Way's outer regions. Such observations provide critical constraints on theoretical models and inform our understanding of how asymmetric explosions unfold. Beyond their astrophysical importance, runaway pulsars also captivate the imagination as potential cosmic explorers. If life or advanced civilizations exist elsewhere in the galaxy, it is tantalizing to consider that these compact stars might serve as natural beacons or navigational aids. Their predictable pulsations can act like cosmic lighthouses, signaling position and time across vast distances. Scientists have proposed using pulsar timing for spacecraft navigation, exploiting the precise arrival times of pulses as a galactic GPS. Runaway pulsars, moving through relatively empty regions of space, might provide especially stable and interference-free timing references. The future of runaway pulsar research is bright. Upcoming facilities such as the Square Kilometre Array, SK, will revolutionize pulsar astronomy, detecting thousands more pulsars and improving measurements of their positions, speeds, and timing. This wealth of data promises to deepen our understanding of supernova physics, neutron star interiors, and galactic structure. Moreover, the synergy of multi-wavelength observations, from radio to X-ray to gamma ray, will paint a more comprehensive picture of how these extraordinary objects interact with their environment. In the grand tapestry of the cosmos, runaway pulsars are threads that weave together the life and death of stars, the violent forces that shape galaxies, and the fundamental physics governing matter at its most extreme. They remind us that the universe is dynamic and unpredictable, where even the remnants of destruction become wanderers, messengers, and cosmic enigmas. Their rhythmic pulses, echoing through space and time, challenge us to listen, to decode the stories of their violent origins, their lonely journeys, and the secrets they carry. As we continue to unravel their mysteries, runaway pulsars will remain symbols of the relentless motion and transformation that define our universe, forever spinning, forever racing into the unknown. As we contemplate the journey of runaway pulsars, another fascinating dimension emerges when we consider their role as laboratories for extreme physics. Neutron stars, the dense cores from which pulsars arise, contain matter compressed beyond anything achievable on Earth. A teaspoon of neutron star material would weigh billions of tons, and the physics governing this ultra-dense matter is still not fully understood. Studying pulsars, especially those speeding through different environments as runaway stars, offers unique insights into the behavior of matter at nuclear densities. Because pulsars emit highly regular pulses of electromagnetic radiation, any minute changes in their spin rate or pulse timing can reveal details about their internal structure and the environment they traverse. For instance, glitches, sudden, tiny increases in spin rate, are thought to be caused by interactions between the superfluid core and the solid crust of the neutron star. Observing such events in runaway pulsars, which may experience different stress and magnetic field dynamics due to their high velocity, helps researchers test competing theories about neutron star interiors. Furthermore, the magnetic fields of runaway pulsars can be extraordinarily intense, reaching up to 10 to the power of 15 Gaussian magnetars, which are a type of neutron star with ultra-strong magnetic fields. These fields influence not only the emission mechanisms, but also the pulsar's interaction with surrounding matter. As a runaway pulsar moves rapidly through varying interstellar environments, its magnetic field can trigger different plasma processes, affecting how and where radiation is emitted. Monitoring these changes provides a natural experiment in magnetohydrodynamics under conditions impossible to recreate artificially. Runaway pulsars also play a role in enriching and stirring the interstellar medium, ISM. As they sweep through space, their winds of high-energy particles collide with gas and dust, injecting energy, momentum, and newly synthesized elements into the ISM. This feedback can affect star formation in nearby clouds, potentially triggering or inhibiting the collapse of molecular clouds into new stars. In this way, pulsars are both the end point of stellar evolution and active agents shaping the next generation of stars, a cosmic cycle encoded in their motion. In recent years, astronomers have identified a few exceptional runaway pulsars exhibiting behaviors that challenge conventional understanding. For example, some pulsars show evidence of changing their pulse profiles or intermittently switching off and on, phenomena that might be linked to their interaction with dense clouds or magnetic reconnection events triggered by their motion. Others have been found with unusual trajectories or located far outside the galactic plane, suggesting complex ejection histories or interactions with other massive objects. The fastest known pulsar, PSR B1508+55, moving at roughly 1,100 km per second, serves as a benchmark for understanding the upper limits of pulsar kick velocities. Its speed not only informs theories of supernova asymmetry but also poses questions about the possible existence of even faster neutron stars. Could there be pulsars hurtling at tens of thousands of kilometers per second, perhaps resulting from exotic mechanisms like interactions in dense star clusters or gravitational slingshot effects near black holes? These remain open questions driving the frontier of high-energy astrophysics. Another compelling mystery surrounding runaway pulsars relates to their detectability and the completeness of our current census. Pulsars emit radiation primarily in radio frequencies, but as they age, their emission can weaken or shift to other wavelengths, making them harder to observe. Additionally, their rapid movement means they can quickly leave regions surveyed by telescopes, effectively vanishing from our catalogs. This suggests that many runaway pulsars remain hidden, wandering the galaxy or intergalactic space unseen. To uncover these elusive objects, astronomers are employing innovative detection strategies. High-sensitivity X-ray and gamma-ray observatories can detect pulsar emissions independent of their radioactivity. Observations of bow shocks in infrared and optical wavelengths also provide indirect evidence of pulsars interacting with the ISM. Combining these multi-wavelength data sets with advanced machine learning algorithms enhances the chances of discovering new runaway pulsars and understanding their distribution throughout the galaxy. The study of runaway pulsars extends beyond the Milky Way. Other galaxies, especially those with high star formation rates and frequent supernova explosions, likely host populations of high-velocity neutron stars as well. Observations using next-generation telescopes, such as the James Webb Space Telescope and the Vera C. Rubin Observatory, aim to detect extragalactic pulsars and their bow shocks. This will allow comparative studies of pulsar populations across different galactic environments, shedding light on universal versus local factors influencing pulsar birth velocities. One of the most intriguing possibilities is that runaway pulsars could eventually escape not only their host galaxy but also the entire galaxy cluster, drifting through intergalactic space indefinitely. While such intergalactic pulsars would be extraordinarily difficult to detect given their faintness and distance, their existence would have profound implications for our understanding of galactic evolution, mass distribution in the universe, and the fate of stellar remnants. In a broader cosmic context, runaway pulsars highlight the dynamic and interconnected nature of the universe. They embody processes that link stellar death to cosmic recycling, gravitational physics to electromagnetic phenomena, and galactic structure to interstellar chemistry. Each pulsar's journey is a story of birth, trauma, survival, and solitary travel, a narrative written in pulses of light across unimaginable distances. As technology advances and observational methods improve, the secrets of runaway pulsars will continue to unfold. Their study challenges our theories, inspires new questions, and pushes the boundaries of human knowledge. The tale of these stellar speedsters is far from over. It is an ongoing saga of cosmic motion and mystery, inviting us to keep watching, listening, and wondering. The journey of runaway pulsars takes on an even more compelling significance when we consider their potential to act as probes of the fundamental nature of gravity and space-time. Because pulsars emit beams of radiation at very regular intervals, they serve as some of the universe's most precise clocks. When a pulsar is in a binary system or moving through regions with strong gravitational fields, tiny variations in its pulse timing can reveal the influence of gravity with exquisite precision. Runaway pulsars, racing through different gravitational environments, present unique opportunities to test Einstein's theory of general relativity and explore potential deviations or extensions to it. Particularly intriguing are pulsars that travel through or near dense regions such as globular clusters or the galactic center, where gravitational fields are more intense and complex. In these environments, pulsar timing can be used to detect gravitational waves, ripples in space-time caused by massive accelerating objects, by measuring minuscule shifts in the arrival time of pulses. Although most gravitational wave detections currently come from ground-based observatories monitoring black hole and neutron star mergers, pulsars themselves form a galaxy-scale gravitational wave detector known as a pulsar timing array, PTA. Runaway pulsars, with their unique trajectories and environments, could augment the sensitivity of these arrays, helping to detect low-frequency gravitational waves from supermassive black hole binaries or other exotic sources. Moreover, pulsars are natural laboratories for studying the equation of state of nuclear matter, a relationship describing how matter behaves at the extreme densities inside neutron stars. Because runaway pulsars might experience different spin-down rates or interactions with external environments compared to stationary ones, their observed properties provide complementary data that refine models of neutron star interiors. Determining the correct equation of state is a major goal in astrophysics and nuclear physics, as it informs our understanding of matter under conditions impossible to replicate on Earth. Runaway pulsars also prompt us to rethink the lifecycle of neutron stars. Traditionally, pulsars are categorized as young or old based on their spin periods and magnetic fields. Yet, the violent ejection and rapid transit through the galaxy could influence their evolution in unexpected ways. For instance, the high-speed movement may strip away or alter the pulsar's magnetosphere, the region dominated by its magnetic field, thereby affecting how it loses rotational energy, and how long it remains detectable as a pulsar. Studying these effects could explain the puzzling variety of pulsar types observed and their sometimes erratic behavior. In addition to the physical insights runaway pulsars provide, their study touches on the broader cosmic narrative of matter distribution and galactic dynamics. When a neutron star is propelled out of its birth galaxy, it carries with it mass, energy, and magnetic fields into the intergalactic medium. While individually small, the cumulative effect of countless such ejections over cosmic time could contribute to the enrichment and magnetization of intergalactic space. This challenges the traditional view of galaxies as closed systems and suggests a more dynamic exchange of matter and energy between galaxies and their environments. The possibility that some runaway pulsars traverse intergalactic space also raises fascinating questions about detectability and observation. In the vast voids between galaxies, the density of gas and dust is incredibly low, reducing interactions that produce observable phenomena like bow shocks or nebulae. Pulsars drifting here would be nearly invisible except for their pulsed emissions, which would be weakened by distance and scattering effects. Detecting such objects would require unprecedented sensitivity and clever observational strategies, possibly involving the next generation of radio telescopes combined with advanced data analysis techniques. Runaway pulsars also intrigue theorists working on exotic physics and cosmology. For example, some have speculated that neutron stars might harbor or produce exotic particles or states of matter, such as quark-gluon plasma or even hypothetical particles linked to dark matter. If runaway pulsars interact with dark matter halos around galaxies or pass through regions of dense dark matter, subtle effects might be detectable in their timing or emission properties. Although speculative, these ideas open exciting avenues for probing the fundamental nature of the universe using astrophysical objects as natural detectors. Another frontier in runaway pulsar research lies in their potential role in multi-messenger astronomy. This emerging field combines observations across electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays to gain a holistic picture of astrophysical events. Runaway pulsars born from supernovae may also be sources of neutrinos and cosmic rays. Tracking their positions and motions in concert with detections of high-energy particles or gravitational signals could unlock new understanding of particle acceleration, nuclear processes, and stellar explosions. Runaway pulsars exemplify the interconnectedness of cosmic phenomena. Their existence bridges the life cycle of stars, the dynamics of galaxies, the physics of dense matter, and the quest to understand gravity and fundamental particles. They embody extremes of speed, density, magnetism, and mystery. Yet, through them, we glimpse the universe's coherence and the ingenuity of human inquiry. As we look ahead, the continued observation and study of runaway pulsars will undoubtedly yield new surprises. The expanding network of observatories across the electromagnetic spectrum, combined with advances in computational astrophysics, will enable more precise measurements and deeper insights. Collaborations between astronomers, physicists, and data scientists will be key to interpreting the complex signals and translating them into knowledge about the cosmos. The story of runaway pulsars is a testament to the ever-evolving quest to understand our universe. From the violent deaths of massive stars to the quiet but relentless journey across the galaxy, these cosmic speedsters challenge our theories, enrich our knowledge, and inspire wonder. Their pulses echo through space and time, inviting us to listen closely to the universe's most extraordinary tales. The continuous motion of runaway pulsars across the cosmic landscape also contributes to an evolving understanding of galactic escape velocities and stellar population dynamics. Every galaxy has a certain escape velocity, the speed required for an object to overcome its gravitational pull and break free into intergalactic space. In the case of the Milky Way, this velocity varies based on location but is estimated to be roughly 550 km per second near the Sun, and higher toward the galactic center. When a neutron star, barely 20 kilometers wide but with more mass than our Sun, exceeds this speed, it becomes a fugitive from its birthplace, destined to travel the void between galaxies indefinitely. Several known runaway pulsars have velocities at or beyond this limit. Their trajectories suggest that some are no longer gravitationally bound to the Milky Way. These stars have effectively become intergalactic wanderers, carrying with them information about the environments they left behind and clues to the violent explosions that gave them their start. Unlike stars that remain nestled within the galactic disk, these pulsars move through regions where they interact very little with ambient gas, making them harder to detect but potentially purer in the signals they emit. Some researchers speculate that these runaway neutron stars might account for a portion of the so-called missing baryons in the universe. Baryonic matter, the ordinary matter made of protons and neutrons, is only partially accounted for in galaxy surveys and cosmic background observations. High-speed neutron stars expelled into the intergalactic medium could be contributing to this hidden reservoir of mass, spread thinly across vast regions and escaping detection due to their small size and faint emissions. If even a small fraction of supernovae produce such ejections, the cumulative population of runaway neutron stars could be significant. Another intriguing avenue of study is the role of binary systems in producing runaway pulsars. When one star in a close binary pair explodes as a supernova, the sudden loss of mass can disrupt the system. If the neutron star receives an additional asymmetric kick from the explosion, it can be ejected at tremendous speeds, while its companion might remain bound in a wildly different orbit, or itself be ejected in the opposite direction. In some cases, both objects are flung into space, leading to a double runaway system. Identifying these pairs and reconstructing their flight paths provides not only a deeper understanding of supernova dynamics but also a rare opportunity to study the aftermath of stellar companionship shattered by cosmic violence. In a few spectacular instances, astronomers have found evidence of isolated high-speed neutron stars that may have once belonged to triple star systems. In such complex arrangements, gravitational interactions during or after a supernova can be even more chaotic, producing exotic outcomes such as the ejection of all components, or the formation of tight binary pulsars still bound despite extreme velocities. These exotic remnants could eventually be sources of gravitational waves detectable by next-generation observatories like the Laser Interferometer Space Antenna, LISA, slated for launch in the 2030s. Beyond individual examples, the statistical study of runaway pulsars is also proving to be invaluable. By modeling the velocities, directions, and birth rates of pulsars throughout the galaxy, researchers can gain insight into the overall structure of the Milky Way's stellar halo and its history of star formation. These studies also help refine our understanding of supernova rates and types, especially since not all supernovae leave behind detectable remnants. High-speed pulsars provide a tangible signature of the invisible population of neutron stars that now roam far from where they were born. The high-velocity nature of runaway pulsars also raises questions about what happens when they eventually encounter other structures in space. For example, a pulsar passing through a dense molecular cloud or a remnant of another supernova may trigger new physical interactions, such as enhanced particle acceleration, localized heating, or even compression of gas that leads to star formation. Although such events are rare due to the vast emptiness of space, they offer a unique natural laboratory when they do occur, allowing scientists to observe how compact objects influence their surroundings long after their birth. Pulsars also serve as remarkable probes for measuring properties of the interstellar medium, ISM, they travel through. As their radiation passes through different regions of space, it is affected by intervening plasma, dust, and magnetic fields. By analyzing the dispersion and scattering of pulses, how certain frequencies are delayed or spread out, astronomers can infer the density, turbulence, and magnetic characteristics of the ISM. Runaway pulsars, especially those with extreme paths crossing different regions of the galaxy, allow for mapping the ISM in 3 dimensions across wide swaths of the galaxy. In the coming decades, advances in machine learning and artificial intelligence will play a key role in identifying and characterizing runaway pulsars. Massive sky surveys and telescope arrays will produce data at an unprecedented scale, requiring automated tools to sift through millions of signals for those faint, rhythmic pulses of neutron stars. Algorithms trained to recognize the subtle patterns and anomalies of pulsar behavior could uncover entirely new classes of high-velocity objects, including pulsars that emit only sporadically or in unusual energy ranges. Moreover, with the increasing international collaboration among observatories, a global pulsar monitoring network is emerging. This effort, including projects like the International Pulsar Timing Array, will allow astronomers to track runaway pulsars with unmatched precision over decades. Such continuous observation opens the door to long baseline timing experiments capable of detecting even the tiniest deviations in pulse regularity, which could hint at the presence of orbiting planets, nearby gravitational wave sources, or unseen companions. As these pulsars travel beyond the gravitational reach of our galaxy, they may encounter structures never before observed, dark matter filaments, intergalactic clouds, or even the outskirts of other galaxies. Each new detection and trajectory offers the potential to reveal something about the unseen architecture of the cosmos. It is conceivable that in the distant future, humanity or its robotic explorers may launch missions guided by pulsar-based navigation, eventually catching up with one of these stellar refugees to study it up close. In many ways, runaway pulsars are cosmic trailblazers. They are the rare few among their kind who break free from the gravitational confines of their stellar neighborhoods, becoming messengers traveling deep into the unknown. Their very existence proves that even the smallest and most compact remnants of stars can defy expectation, race against the pull of galaxies, and become enduring beacons of cosmic history. With each pulse they emit, sometimes from the galactic outskirts, sometimes from interstellar silence, they whisper clues to the universe's most extreme processes, its turbulent past, and perhaps, its unfathomable future. Yet as these cosmic wanderers continue their silent odyssey through the void, another fascinating aspect of runaway pulsars emerges: their relationship with the broader evolutionary arc of galaxies. While they are born in explosive cataclysms within stellar nurseries, often in spiral arms or dense clusters, many of them end up in the outer galactic halo, or even beyond, effectively becoming part of the population that maps a galaxy's outermost reaches. In this role, runaway pulsars serve as tracers of galactic structure and motion, helping scientists map out the gravitational potential and shape of the galaxy itself. By studying the trajectories of these neutron stars, astronomers can estimate the distribution of mass, both visible and invisible, within and around the Milky Way. Because pulsars are compact and resistant to tidal stripping or evaporation, unlike loosely bound star clusters, they offer a relatively stable and long-lived probe into the dynamics of our galactic halo. The velocity and direction of their motion are influenced by the gravitational effects of both baryonic matter, stars, gas, dust, and dark matter, the elusive substance that dominates the universe's mass budget. If a pulsar appears to decelerate or change course ever so slightly, that shift might betray the gravitational tug of a massive, unseen clump of dark matter. Runaway pulsars may also illuminate a subtler, quieter mystery: whether the outer halo of the galaxy is as smooth as models predict. Some simulations suggest the halo should contain ripples, streams, or clumps left behind by past galactic mergers. As pulsars travel through this chaotic terrain, their paths might curve or scatter in unexpected ways, revealing the underlying structure of the halo in ways no other object can. In this sense, each pulsar is like a mariner tracing the hidden contours of a dark cosmic ocean, mapping the galactic boundaries we cannot yet see. The immense velocities of some runaway pulsars push the boundaries of what we thought was physically possible from single supernova events. Consider a pulsar traveling at over 1,000 kilometers per second. It challenges the limits of what can be explained by conventional asymmetric explosions. To reach such speeds, the pulsar must have been accelerated by forces far greater than a typical kick. This opens speculation to alternative theories, such as the presence of extremely asymmetric neutrino emissions, magnetic reconnection events of terrifying intensity, or interactions with rapidly spinning progenitor stars that channel momentum unevenly. Some models even entertain more speculative ideas, like the existence of exotic matter in the supernova core that could momentarily warp spacetime, producing gravitational asymmetries large enough to hurl the pulsar outward. While these scenarios remain theoretical, they are not beyond the scope of modern astrophysics. The extreme conditions inside supernovae are so poorly understood that runaway pulsars could hold the key to unlocking new physics, much like how anomalies in planetary orbits once led to the discovery of Neptune, or even the rise of Einstein's theory of general relativity. These ideas gain more traction when we consider another class of neutron stars known as magnetars. These are pulsars with magnetic fields 1,000 times stronger than ordinary pulsars, so strong, in fact, that their field can distort atomic structures and release bursts of gamma rays so powerful they can affect satellites orbiting Earth. If a magnetar is also a runaway, its interaction with the galactic environment becomes even more dramatic. Traveling at high speed through a plasma-rich region, it could generate magnetic shocks, jets, or even light echoes that can be detected across vast distances. In some rare instances, runaway magnetars may pass close enough to a star-forming cloud to influence the birth of new stars. Their powerful winds and radiation could compress parts of the cloud, initiating gravitational collapse in pockets that were previously stable. Alternatively, the opposite might happen. Radiation might heat and disperse the cloud, quenching star formation instead. In either case, the pulsar becomes an agent of change long after its own birth, a stellar ghost shaping the destiny of stars yet to be born. There's also the tantalizing idea that some runaway pulsars may possess planetary systems. Though planets are rare around neutron stars due to the extreme conditions surrounding their formation, a few have been discovered. These planets are likely second generation, formed from fallback material after the supernova, or captured during complex gravitational encounters. Now imagine a planetary system flung into interstellar or intergalactic space, bound to a neutron star hurtling through the cosmos. What kind of night sky would such a world see? How would its surface radiation compare to Earth's? Could life, in any form, ever survive in such an environment? Even if life as we know it could not, the presence of such a system challenges our understanding of planet formation and survival. It also raises the faint but profound possibility that material from such systems, dust, gas, or even dormant microbes, could one day reach other planetary systems, traveling like cosmic spores across the galactic void. In this sense, runaway pulsars may not only be relics of stellar death but unlikely vessels for the scattering of planetary building blocks across time and space. Looking deeper into the future, pulsars may even help humanity navigate its own journeys through space. Their predictable pulses make them ideal for galactic navigation systems. Already, space agencies like NASA are experimenting with pulsar-based navigation, XNAV, which uses pulsar timing as a kind of interstellar GPS. If humanity ever ventures beyond the solar system, our spacecraft may one day orient themselves using the signals from runaway pulsars, cosmic lighthouses that, despite their lonely paths, could help us find our way among the stars. The mystery of runaway pulsars is not just about velocity or explosions, it is about what it means to survive an event meant to destroy you. These are stellar remnants that have been hurled from their homes by violence, yet persist, emitting their rhythmic light into the cold dark. They are survivors, wanderers, explorers, and messengers. Their stories are written in radio waves and gamma rays, in shock fronts and bow shocks, in twisted fields and timed pulses. We may never catch one. We may never know the exact path that led to their launch, but we can follow their light, piece by piece, and let their journey mirror our own, an endless voyage into the unknown, searching for meaning, connection, and cosmic understanding. And so the pulses continue, like distant heartbeats echoing across the grand silence of space. Every signal we capture from a runaway pulsar is not just a point of data, it's a timestamp from a cosmic traveler, a message dispatched years, centuries, or even millennia ago, arriving only now to tell us a story we're still learning how to read. These messages are embedded in complex waveforms, subtle variations in intensity and timing, and occasionally, strange anomalies that challenge our existing models. It's in these irregularities, the stuttering of a pulse, the unexplained shift in frequency, the sudden silence followed by reactivation, that some of the greatest mysteries still lurk. Take, for instance, the phenomenon of pulsar nulling, where a pulsar seemingly stops emitting pulses for a period ranging from seconds to days before resuming activity. In some runaway pulsars, these nulls have been detected mid-transit across regions of differing galactic density. Is it possible that interactions with interstellar matter, magnetic anomalies, or changes in the pulsar's internal structure can cause this? Or is something even more exotic at play, like quantum vacuum effects or interactions with hidden dimensions as theorized in some advanced physics frameworks? These aren't idle questions. Each enigmatic pulsar pushes the boundaries of what we know about matter, energy, and even time. Because pulsars are among the most regular natural phenomena known, when they misbehave, it's a sign that something deeply unusual is occurring. Perhaps in these deviations lie the keys to concepts we've only begun to theorize: quantum gravity, extra-dimensional physics, or even the nature of consciousness itself, as some speculative thinkers have proposed when discussing quantum coherence in extreme environments. Then there's the question of the oldest runaway pulsars. As they move further from the galactic disk and their pulses slow with age, they eventually reach a point where they die, as observable pulsars. Their radio beams no longer sweep past Earth, but their cores remain, cold and quiet neutron stars continuing their journey invisibly. Could we, with future X-ray or gravitational wave technology, detect this silent majority of runaway remnants that populate the galactic outskirts like ghost ships from ancient battles? The detection of these long-dead pulsars might open up entirely new fields of study. We might trace how the oldest neutron stars have evolved internally, what hidden structures or states they've settled into, and how they've interacted with the cosmic web beyond the Milky Way. These objects could even serve as ancient records of the galaxy's past, their very composition offering clues to the chemical conditions billions of years ago. In a related line of inquiry, scientists are now exploring whether runaway pulsars could serve as indirect indicators of the rate of black hole formation. Since both neutron stars and black holes result from supernova explosions, the ratio between them, especially when factoring in runaway velocities, can reveal much about the thresholds of stellar collapse. If we discover more neutron stars than expected among runaway objects, it might suggest that slightly less massive progenitors are more likely to survive as pulsars than collapse into black holes. Conversely, an unexpected lack of high-velocity neutron stars could hint that black hole formation is more common than previously assumed, or that some black holes too are being kicked into intergalactic space, rendering them almost completely undetectable. Imagine, then, a black hole analog to the runaway pulsar, a silent, invisible object traveling at hundreds or thousands of kilometers per second, warping space in its wake but leaving no direct signal behind. Such objects, if they exist, would be among the most elusive inhabitants of the cosmos. But perhaps the study of runaway pulsars, their dynamics, origins, and behaviors, could give us a path to identifying these dark travelers by association, gravitational lensing effects, or faint accretion signatures from the interstellar medium. There's another dimension to the runaway pulsar narrative that is philosophical, almost mythological. These are not just stars. They are remnants of explosions, survivors of destruction, solitary voyagers thrown from their stellar families, wandering alone across millions of light years. Their stories echo ancient human tales of exile, of heroes cast out into the wilderness only to become beacons of hope or harbingers of hidden truths. In the quiet discipline of astrophysics, it's easy to forget that we are emotional beings drawn to the mysteries of the universe not just for knowledge, but for meaning. Runaway pulsars, then, occupy a special place in the cosmological tapestry. They blur the boundaries between categories, alive and dead, bound and free, seen and unseen. They inhabit the liminal space between galactic memory and cosmic oblivion. And as such, they invite us to see the universe not just as a machine of matter and laws, but as a living storybook, where each pulse is a word in a sentence we are just beginning to read. The tools we build to chase these stars, radio telescopes arrayed across continents, space-based observatories orbiting our planet, deep learning algorithms processing terabytes of data, are extensions of this human yearning to listen to the cosmos. And sometimes, if we're lucky, a runaway pulsar answers. Sometimes it tells us something we've never heard before. A signal that challenges our assumptions, bends our models, or opens a door to deeper mysteries. It reminds us that science isn't just about certainty, it's about wonder, humility, and the courage to ask questions no one has ever dared to ask. And so, the hunt continues. Across the black canvas of the night sky, these rogue beacons still flash. Some are flying away faster than the escape velocity of their galaxies. Some may have already reached the intergalactic void, where they drift between ancient galactic islands, pulsing for no one but themselves. Others may be on paths that will intersect with neighboring galaxies millions of years from now, becoming the first neutron stars in Andromeda that didn't originate there. With each new discovery, each precisely timed pulse, each arc traced across the galactic map, we get a little closer to understanding how the cosmos balances chaos with order, violence with silence, and death with persistence. The story of runaway pulsars is far from over. In fact, it may only just be beginning. And as we venture further into this unfolding cosmic narrative, we come to appreciate that runaway pulsars are not merely solitary objects flung into deep space by accident. They are active participants in the galactic ecosystem. Their high-speed passage through various regions of space not only shapes the interstellar medium, but also leaves behind distinct, sometimes eerie signatures, bow shocks, trails of energized particles, and in rare cases, gravitational disturbances that ripple across space like subtle fingerprints of a silent traveler. These bow shocks, in particular, are some of the most visually striking and scientifically rich phenomena associated with runaway pulsars. As a pulsar tears through the interstellar medium at supersonic speeds, it compresses gas and dust in front of it, creating a shockwave shaped like a crescent or a comet's tail. These formations, often visible in infrared or X-ray wavelengths, are not just beautiful, they're incredibly useful for measuring the pulsar's speed, direction, and interaction with its environment. In some cases, the bow shock glows with high-energy particles accelerated by the pulsar's magnetic field, forming what's known as a pulsar wind nebula. Pulsar wind nebulae, especially those formed by runaway pulsars, are laboratories for extreme physics. Within these nebulae, particles are accelerated to relativistic speeds, close to the speed of light, by electromagnetic processes so powerful that they mimic conditions in the earliest moments of the universe. Observing these interactions helps scientists study shock acceleration, magnetic turbulence, and particle diffusion in ways that terrestrial experiments can't replicate. And with every bow shock we map, we gain insight into the composition, density, and structure of the space the pulsar is moving through, revealing the hidden architecture of the galaxy. But there's more. Some runaway pulsars may have originated in binary systems that were not just companions to stars, but to black holes or even other neutron stars. When such a system is disrupted by a supernova, the surviving companion, now a runaway, may retain evidence of the gravitational and magnetic torment it endured. This might show up as unusual spin rates, distorted magnetic fields, or even disrupted timing sequences. These clues can reveal the story of past binary interactions, making each pulsar a kind of time capsule preserving the memory of its stellar dance. Even more astonishing is the possibility that some runaway pulsars might come from exotic environments, like globular clusters, the ancient, densely packed star cities orbiting the galactic core. The gravitational conditions in such clusters are extreme, and interactions between stars and remnants are frequent and violent. A neutron star ejected from a globular cluster might carry with it traces of multiple collisions, complex spin histories, or unusually enriched elemental signatures. These travelers would be not just runaways, but ancient messengers from the earliest epochs of galactic formation, bearing witness to the cosmic ballet that played out in the Milky Way's youth. And as astronomers refine their instruments, more of these travelers are being found. The European Space Agency's Gaia mission, which maps the positions and motions of over 1 billion stars, has been instrumental in identifying high-velocity stellar objects, including potential runaway pulsars. By cross-referencing Gaia data with radio and X-ray pulsar catalogs, researchers can pinpoint which neutron stars are moving unusually fast and trace their paths back to their likely origins. Some of these backtraced trajectories point to known supernova remnants, or stellar clusters, but others lead to empty space, suggesting either ancient explosions whose traces have long since dissipated or violent events that left no visible scar. The James Webb Space Telescope and upcoming next-generation observatories like the Square Kilometre Array, SKA, promise even more. These powerful instruments will allow us to detect fainter, more distant runaway pulsars, perhaps even in other galaxies. Imagine being able to track a neutron star as it exits the Milky Way and begins its voyage across intergalactic space, a solitary object, launched by cataclysm, carrying with it the last whispers of a long-dead star. And that intergalactic voyage, once a mere poetic idea, is now an active area of study. Some runaway pulsars travel at speeds sufficient to break free of the gravitational pull of the Milky Way entirely. These hypervelocity pulsars are among the fastest-moving objects in the known universe, their speeds rivaling those of galaxy-scale gravitational interactions. Once they cross the galactic boundary, they enter the great cosmic wilderness between galaxies, a space so vast and empty that even light takes millions of years to cross it. What happens to a neutron star in this realm? Does it encounter pockets of gas that faintly light up its bow shock once more? Or does it simply glide through the darkness, its signals growing ever fainter, destined to echo unanswered for eons? This idea, the infinite journey of a hypervelocity pulsar, brings us face to face with one of the most haunting and beautiful possibilities in all of astrophysics, that there are messengers from our galaxy, whispering their final pulses into the void, far beyond the reach of any receiver, beyond any star, beyond any memory. In a universe that seems destined to expand forever, with galaxies drifting apart and stars eventually dying out, these runaway pulsars might become the last active objects from the Milky Way still operating, still pulsing, still telling their story, long after everything else has gone silent. And maybe, just maybe someone, or something, else will hear them. As we meditate on the profound silence of deep space and the lonely journey of these cosmic exiles, a compelling question arises. What if runaway pulsars aren't just byproducts of stellar violence, but essential components of the universe's long-term evolution? It's easy to view them as anomalies, as side effects of explosive endings, but their presence and behavior may be intricately tied to how galaxies recycle matter, transfer energy, and shape cosmic structure across eons. A neutron star, despite its tiny size, often just 20 kilometers in diameter, is an immense reservoir of mass, energy, and magnetic intensity. When propelled at high velocities, it becomes a bullet of condensed matter, an agent capable of piercing through clouds of interstellar gas and stirring up regions that may have remained dormant for millions of years. This process of kinetic interaction with the interstellar medium can seed new turbulence, cause compression, and in rare cases, ignite new waves of star formation. In essence, runaway pulsars may serve as mobile catalysts, micro-level architects guiding the macroevolution of their galactic environment. This is particularly intriguing when considered on a cosmic timescale. Galaxies are not static, they are in constant flux, devouring smaller galaxies, shedding stars, and cycling gas between hot halos and dense disks. In this grand cycle, neutron stars, especially the fast-moving ones, act as dynamic agents of entropy and order, disrupting the equilibrium of molecular clouds or enriching regions with heavy elements. These stars, forged in death, are ironically engines of rebirth. Their passage could mark the invisible scaffolding upon which future stars will form, and perhaps even future civilizations will arise. And yet, the influence of a runaway pulsar isn't always nurturing. There's a destructive side too. A neutron star's radiation, especially if it is still actively emitting X-rays or gamma rays, can sterilize vast swaths of nearby space. A close pass to a forming planetary system could erase fragile atmospheres, disrupt protoplanetary disks, or hinder the chemistry required for life. In this sense, runaway pulsars are not just wayward travelers, they are potential harbingers of both creation and annihilation. We might even imagine a distant future, billions of years from now, when galactic collisions are long over and stellar formation has largely ceased. In this late-stage universe, as stars burn out and galaxies grow dim, the only remaining sources of active radiation may be pulsars, some stationary, some still roaming the void. These beacons, scattered across space like forgotten lighthouses, could define the final chapters of observable cosmic activity. Runaway pulsars may be among the last voices in a dying universe, whispering across the silence. But here's another twist, one grounded more in theoretical physics than observational astronomy. Some physicists have proposed that in extremely rare conditions, neutron stars could collapse further, not into black holes, but into more exotic forms of matter. Quark stars, for instance, are a hypothetical class of stellar remnants composed entirely of quarks, the fundamental building blocks of protons and neutrons. These objects, if they exist, would be even denser than neutron stars and could behave in radically different ways. Now consider the implications if a runaway pulsar underwent such a transformation mid-flight. The change could produce a sudden burst of gravitational waves, neutrinos, or gamma rays, signatures of a previously unknown class of stellar death. And if such an event occurred in intergalactic space, away from the noise of other astrophysical sources, we might be able to isolate and analyze it in extraordinary detail. These hypothetical runaway quark stars could help us test theories of quantum chromodynamics, the behavior of matter at the smallest scales, and the fate of degenerate matter under unimaginable pressures. Moreover, what if some runaway pulsars aren't alone? While most known neutron stars are solitary, there's always a chance that a binary system survived a partial disruption, two compact objects, bound by gravity, racing through space together. A runaway binary neutron star system would be a gravitational time bomb, eventually spiraling into a collision and creating one of the most powerful known events in the universe, a kilonova. Kilonovae are responsible for producing a significant portion of the universe's heavy elements: gold, platinum, uranium. If one were to occur in the far reaches of intergalactic space, the resulting ejecta would seed elements into the cosmic void, creating floating reservoirs of complex matter that may one day be swept into forming galaxies. It's a stunning realization. Runaway systems, thought to be lost or exiled, might end up sowing the seeds of elemental complexity across the universe in the most unexpected places. And the role of pulsars in human progress shouldn't be underestimated either. Already, millisecond pulsars are so precise in their rotational timing that scientists have proposed using them to establish a cosmic clock, a way to define universal time across vast distances. The concept, known as pulsar timekeeping, could help spacecraft navigate autonomously through the galaxy, syncing their instruments to the reliable ticks of pulsars rather than relying on Earth-based communication. More provocatively, the idea has even made its way into interstellar messaging. The famous Pioneer and Voyager spacecrafts include plaques and records that point toward Earth's location using a map of pulsar positions. These maps assume that any sufficiently advanced civilization capable of understanding the pulsar timing method would be able to decipher where and when the spacecraft originated. It's a deeply poetic idea, that in the future, some intelligence adrift in space might come across a signal from Earth and trace it using the light of a runaway star, pulsing from the galactic dark. Runaway pulsars, in that sense, may be more than physical objects. They are cosmic timekeepers, messengers, keys. And perhaps, they are reminders that even the most violent beginnings can give rise to paths of enduring significance. They embody resilience, born in destruction, exiled into loneliness, yet persistent in their motion, consistent in their signal. We chase them across the night sky not just to understand them, but to understand ourselves. They are reflections of humanity's own desire to move forward, even when cast out by catastrophe, even when the path is unlit, even when the universe seems cold and indifferent. And so we listen. We watch. We wait. Somewhere, in the silence between the stars, a new pulsar may be born tonight. Somewhere, another may be quietly slipping beyond the galactic edge, its beam aimed forever outward, a final cry into the infinite dark. And so the pulse goes on, ticking like the final seconds of a forgotten cosmic watch, echoing through time, reaching across distances too vast for human imagination to contain. These runaway pulsars, like the footsteps of celestial nomads, leave behind a cosmic trail that is both ephemeral and eternal. They do not belong to any one place. Not to the supernova that birthed them, nor the galaxy they abandoned, nor the empty intergalactic sea they now traverse. They belong to motion itself, to exile, to persistence. What makes their story all the more compelling is that, despite their distance, despite the unimaginable isolation, their signals reach us. They are audible to our machines, decipherable to our math, and inspiring to our minds. With each detection of a new high-velocity neutron star, we gain not just a data point, but a chapter in the long and unfinished book of the universe. A book that has no known ending, and perhaps no beginning as we traditionally understand it. Consider how we identify a runaway pulsar. Often it begins with a subtle clue, a timing irregularity, a Doppler shift, a positional discrepancy. These are faint hints, tiny footprints in the gravitational sand. But when analyzed in tandem with astrometric data from telescopes like Gaia and timing data from pulsar arrays, they come together to form a complete portrait of a traveler. By measuring its velocity, its spin-down rate, its direction of motion, and its potential origin point, we reconstruct the path of a star long after it has left the scene of its creation. It's detective work on a galactic scale. Imagine piecing together the story of an object that may have exploded out of its birthplace 100 million years ago. And yet we do. We calculate the location of the supernova remnant that may no longer exist. We estimate the gravitational nudge from a long-lost companion. We theorize about the inner conditions of the progenitor star. All to understand how this one neutron star came to be sprinting through the stars faster than almost anything else known. And in doing so, we begin to uncover trends. Runaway pulsars tend to exhibit particular characteristics, unusually high speeds, often above 1,000 kilometers per second, unusually aligned magnetic axes, and in some cases, peculiar emission properties that don't match standard pulsar models. Some appear to rotate more slowly than expected, suggesting that their magnetic braking was somehow altered by the kick they received. Others seem to emit in erratic patterns, almost as if their pulse was disrupted during ejection. This leads to the tantalizing possibility that runaway pulsars may experience internal changes from the trauma of their creation. Imagine the violent birth of a neutron star, an imploding core, a bouncing shockwave, asymmetric jets of neutrinos and matter, a searing blast that doesn't just hurl the object into space but deforms its very structure. If neutron stars are the densest states of matter before black hole collapse, then perhaps the birth kick permanently alters the arrangement of quarks within. Perhaps every runaway pulsar is internally unique, its atomic lattice frozen in a twist that could never be repeated. And perhaps, in those anomalies, lies a key to new physics. Already, neutron stars serve as laboratories for exotic states of matter, superfluids, superconductors, and possibly quark-gluon plasma cores. A pulsar flung at high velocity might be stressed in a way that reveals rare transitions, some fleeting burst, some unusual cooling rate, or an unexplained thermal gradient that contradicts current models. These stars may, in their loneliness, teach us more than stars bound in stellar cities ever could. There's also the philosophical aspect to all of this, which no astrophysical analysis can quite capture. There is something deeply haunting and beautiful in the idea that a star, destroyed in a supernova, leaves behind a child, small, dense, burning with magnetic energy, and that this child is then hurled across the cosmos, alone. That loneliness speaks to something in us. These stars are symbols of survival through catastrophe. Symbols of direction in a universe that has none. symbols of light pulsing into a dark unknown. And we, bound to our tiny planet, follow them. We build vast arrays of radio dishes, we launch satellites into the void, and we tune our instruments to the faintest whisper of a distant pulse. Some of those pulses have traveled for thousands of years before reaching us. And we don't even know if we are the first to hear them. Perhaps civilizations long gone heard those pulses first. Perhaps others yet to come will hear them long after Earth is dust. Runaway pulsars remind us that the universe isn't still. It's dynamic, aggressive, restless. Stars don't always stay where they're born. They wander. They race. They run. And in doing so, they bring new meaning to the concept of motion, not just physical, but existential. These objects are in exile, yes, but in their exile, they create new beauty, new science, new stories. And the stories are far from over. We haven't even fully explored the possibility that some runaway pulsars may be interacting with dark matter. As they pass through regions of higher dark matter density, perhaps near the galactic halo or in intergalactic filaments, they could experience minute accelerations or energy losses that we haven't yet detected. Studying these interactions could open entirely new channels of dark matter research, especially if the pulsar's behavior changes in measurable ways. There is also a theoretical consideration involving gravitational waves. While it's usually binary neutron-star mergers that dominate this field, a rapidly spinning runaway pulsar with a non-uniform shape could emit continuous gravitational waves. These would be incredibly faint, but detectable by future observatories like LISA or enhanced versions of LIGO. Capturing one of these signals would be revolutionary, not only proving that isolated neutron stars can radiate gravitational energy, but also giving us direct insight into their internal deformations. And what of planets? Yes, planets. Some pulsars are known to have planetary systems, possibly formed from fallback material after the supernova. If a pulsar with planets becomes a runaway, what happens to those planets? Do they remain bound in a tightly knit dance around their neutron star host, flung together into the blackness of space? Could a world orbiting a runaway pulsar harbor the conditions for life, perhaps even evolve in ways we can't yet imagine, using the pulsar's steady rhythm as a kind of clock? It's the ultimate science fiction setup, a planet orbiting a pulsar streaking through the cosmos, its surface lit not by a sun, but by magnetospheric pulses. If such a world exists, it would experience time, seasons, and day-night cycles unlike any other. Its sky would be a river of galaxies. Its gravity tides would be distorted. Its evolution would be driven by a source of light that isn't light at all, but radiation. And so we circle back. To pulses. To stars that died yet still speak. To motion that refuses to slow. To stories that refuse to end. Runaway pulsars are more than astrophysical curiosities. They are signals of change, markers of cosmic violence, relics of forgotten explosions. But they are also the future's key, pulses echoing across eternity, leading us, if we are bold enough, deeper into the uncharted mystery of the cosmos. And so the saga of runaway pulsars stretches further into the infinite dark, beckoning us toward even deeper questions about the fabric of our universe. These cosmic sprinters, hurled into the galactic outskirts and beyond, become emissaries not only of astrophysics but of metaphysical thought. What they represent goes beyond motion or mass or magnetism. They represent the persistence of signal against silence, of pattern against chaos, of knowledge in a sea of mystery. As our technology advances, so does our ability to trace these elusive objects. Instruments like the Square Kilometer Array, SKA, still under development, promise to revolutionize pulsar astronomy by detecting thousands, perhaps tens of thousands, of previously unknown pulsars. Among them, we expect to find even more runaways, hidden within the noise of deep space, waiting for their signatures to be decrypted. These new discoveries will allow astronomers to model the population statistics of high-velocity pulsars in unprecedented detail, and more precisely infer how often and in what ways stars are ejected from their birthplaces. The data won't just improve our catalogs, it will refine our understanding of stellar evolution. Current models of supernova mechanisms are riddled with uncertainties. Why do some neutron stars receive powerful kicks, while others remain relatively still. What determines the direction and magnitude of these velocities? Is it purely asymmetry in the explosion, or does it also depend on the pre-supernova structure, binary interactions, or even neutrino dynamics? The more runaway pulsars we track, the better we can reverse engineer their origin stories. But let's push further. Let's go to the edge, literally, to where some runaway pulsars are now crossing the boundaries of the Milky Way itself. The galactic escape velocity in our region is around 550 km per second, yet some pulsars are observed moving much faster, some at nearly 1,000 km per second. This means they're on trajectories that will take them into intergalactic space, never to return. They are leaving the galaxy behind like a message sealed in a bottle and cast into an endless cosmic ocean. What becomes of these galactic refugees? The vast expanses between galaxies are not completely empty. They are laced with the faint fog of the intergalactic medium, with scattered atoms and ancient photons stretching back to the dawn of time. A runaway pulsar drifting through this emptiness may travel for billions of years without ever encountering anything substantial again. It will spin down, grow cold, and ultimately fade to a quiet neutron star, or, eventually, a black dwarf, a theoretical end-stage object that is so cold and dead it emits no radiation. But even in death, it carries its legacy. If we could track such a pulsar over that unimaginable distance and time, we'd witness a complete stellar life cycle in motion. From birth in a luminous supernova, to a fiery pulse racing through the galaxy, to a silent end in the dark. It would be, in a sense, the story of the universe itself: creation, motion, decay, and silence. And yet, in this silence, something astonishing may still occur. Consider the idea of gravitational capture. If a runaway pulsar passes close enough to a rogue planet, brown dwarf, or even another galaxy, it could become gravitationally bound once again. The thought of a runaway star being rescued by a distant, passing mass may seem romantic, but it's a physically plausible scenario. Over billions of years, chance encounters accumulate. A pulsar fleeing one galaxy might eventually be caught in the gravity well of another, becoming part of a new star system in an alien cosmic environment. This possibility adds a strange and beautiful twist to the narrative: runaway pulsars as intergalactic adoptees, bringing their ancient signals into new gravitational homes. If life exists elsewhere, in some distant galactic neighborhood, perhaps they too observe a strange pulsing light moving across their skies, a visitor from another galaxy, bearing the echoes of a supernova that happened before their own world was born. We should also not ignore the potential of these objects in terms of long-term navigation and astrophysical utility. Their predictable pulses make them ideal fixed references for starships of the future. While light from stars is affected by dust and interstellar refraction, pulsar timing cuts through the clutter. A civilization capable of spacefaring over thousands or millions of light years could build a galactic GPS using these distant beacons. Already, NASA's NICER mission aboard the International Space Station has tested the use of X-ray pulsars for autonomous navigation in space, a technology known as XNAV. In the distant future, when humans or their descendants, or completely different sentient beings, roam the stars, they may rely on these pulses as both guides and relics. Imagine a vessel traveling to the Andromeda Galaxy, navigating not by the constellations of Earth but by the ticking of a pulsar that was once flung from the Milky Way a billion years earlier. The same object that once marked catastrophe may now mark safe passage. And what if we took this idea even further? What if we began seeding the galaxy with our own artificially modulated pulsar-like signals, coded pulses broadcast from long-lived probes stationed near neutron stars, designed to transmit data over millions of years? We could use natural pulsars as cosmic clocks and artificial transmitters as time capsules. Runaway pulsars, especially, would be ideal carriers, unchained, unstoppable, and widely distributed. In this way, runaway pulsars could become the backbone of an interstellar archive, a moving web of knowledge cast across the stars, a galactic internet operating on relativistic timeframes. They would be our messengers, carrying the legacy of intelligent life far beyond its cradle, enduring even if civilizations fall. This concept also ties into something broader: the search for extraterrestrial intelligence. If another species wanted to send a signal across deep time and space, they too might have harnessed the reliable beat of a pulsar. Perhaps some of the anomalies we observe in pulsar emissions aren't natural at all, but artifacts of modulation, encryption, or directed communication. It's a long shot, yes, but it's a possibility grounded in scientific curiosity and imagination. So, here we are, runaway pulsars, born in fire, ejected by violence, drifting through darkness, may hold the keys to our most profound quests. They are navigators, timekeepers, destroyers, and creators. They embody the paradoxes of the cosmos, permanence and change, chaos and order, silence and signal. And as long as we continue to look up, listening to those faint cosmic heartbeats, we will find, in the Runaways, a story of motion, mystery, and meaning. The legacy of runaway pulsars doesn't end with their astonishing speed or their place in our cosmic narrative. It deepens with every nuance of their journey, every interaction they have with their environment, and every signal we detect from their spinning cores. Even as these neutron stars rocket away from their birthplaces, they leave indelible imprints upon the galaxies they depart, shaping space in their wake like the ripples of a stone tossed into a still pond. And while much of their story plays out far from our eyes, some of the most profound revelations about the universe may lie hidden within their faint, flickering pulses. When we examine the precise characteristics of runaway pulsars, we find anomalies that force us to question long-standing models of physics. Many of these neutron stars move through the galaxy with velocities that seem implausible based on known supernova dynamics alone. This raises the possibility of multiple, possibly overlapping mechanisms responsible for their acceleration. Could they be interacting with exotic fields or previously unknown forces in the early milliseconds following core collapse? Could magnetic fields, quantum chromodynamics, or even asymmetries in neutrino emission play a larger role than we currently understand? In fact, neutrino-driven kicks are one of the most promising theoretical explanations for the runaway phenomenon. During a core collapse supernova, an extraordinary number of neutrinos are released, as many as 10 in a matter of seconds. These ghost-like particles usually pass through matter unnoticed, but in the dense environment of a collapsing star, even neutrinos can deposit momentum. If there's any slight asymmetry in the neutrino outflow, perhaps due to a misalignment in the magnetic field or uneven material fallback, it could give the nascent neutron star a substantial push. This theory aligns well with some of the observed velocities, but it remains difficult to confirm directly, due to the elusiveness of neutrinos and the complexity of modeling such explosive events in detail. Other models involve the role of binary companions. In binary systems, the dynamics become even more chaotic. If a star in a close binary goes supernova, the explosion can disrupt the gravitational dance, flinging the companion away or, alternatively, accelerating the neutron star remnant to extreme velocities. In some cases, both may be ejected in opposite directions, each becoming a runaway in its own right. Observing these disrupted binaries, and tracing their motions backward through time, offers one of the most direct ways to test the mechanics of these cosmic expulsions. Some runaway pulsars have even been linked back to runaway OB stars, suggesting shared origins in disrupted binary or multiple systems. This kind of forensic astronomy, tracing the trajectory of stars across tens of thousands of light years and millions of years, is immensely complex, but also incredibly rewarding. With precise motion data from missions like Gaia, astronomers can rewind the motions of stars, pulsars, and stellar remnants to locate the potential sites of supernovae that occurred long before humanity walked the Earth. These reconstructions allow us to build detailed simulations of the galaxy's stellar life cycles, mapping not just where stars are born, but where they go after their deaths. And what of the trails they leave behind? As runaway pulsars plow through the interstellar medium, they create bow shocks, curved comet-like shock fronts where their magnetic winds collide with ambient gas and dust. These structures, detectable in X-rays and infrared, offer visual fingerprints of a pulsar's speed and environment. In some cases, they stretch for dozens of light years, illuminating regions of space that would otherwise remain invisible. These glowing shock waves are not just scientifically valuable, They are visually stunning, representing some of the most evocative images in astrophysics. Even more curiously, some of these bow shocks have irregular shapes or unexpected orientations. These anomalies may point to complex magnetic field geometries, interactions with dense interstellar clouds, or variations in the pulsar's wind pressure over time. Each oddity is another piece of the puzzle, another hint that these stellar outcasts are far more complex than simple point-like sources of radio pulses. On a quantum level, runaway pulsars may also present unique opportunities to probe the nature of matter under extreme conditions. Neutron stars in general are cosmic laboratories for the densest known form of matter before black hole collapse, but runaway pulsars, due to their high velocities and potential isolation, may evolve differently. Could the immense pressures and accelerations experienced during ejection lead to rare forms of matter, like color superconducting quark matter, or even hypothetical states such as strange matter? If we could detect a sudden change in a pulsar's timing or spectrum that coincided with such a phase transition, it would revolutionize not only astrophysics but fundamental particle physics. Now imagine this: a runaway pulsar born in the dense core of a supernova, ejected at over 1,000 km per second, blasting through the galaxy, shedding a bow shock and detectable emissions across multiple wavelengths, gradually spinning down and cooling, then, billions of years later, transitioning into an exotic new phase of matter never before seen. And from a lonely point of the cosmos, the remnant pulses out a strange, irregular rhythm, one that carries within it the fingerprint of quark deconfinement. That's not just science fiction, it's within the scope of future observation. Then we come to a particularly tantalizing possibility, that some of these runaway pulsars may be harboring secrets about black holes. If a pulsar originated from a binary system where its partner collapsed into a black hole, their interaction could lead to gravitational slingshot scenarios. Depending on the mass, spin, and separation of the two objects, it's theoretically possible for the pulsar to gain extraordinary speed from such a near escape. In the process, gravitational wave bursts might be emitted, brief flashes of space-time distortion carrying energy across the universe. If detected, these signals could provide a completely new window into how runaway pulsars are flung into interstellar exile. Moreover, the detection of such interactions could be instrumental in understanding the life cycles of black holes and neutron stars and binary systems, particularly those that never merge. Unlike the dramatic mergers that produce gamma-ray bursts and gravitational waves detectable by LIGO, these near-miss interactions leave behind only motion that we can trace and decode. The pulsar's velocity, combined with the absence of its companion, would tell a silent story of a cosmic flirtation that ended in a hasty retreat. What runaway pulsars offer is not just a look into the past, but a promise of discovery in the future. Their very nature forces us to reach, across disciplines, across light years, across time itself. They demand better models, more precise instruments, and deeper theoretical work. They challenge our assumptions about how stars live and die, and what remnants they leave behind. They compel us to redefine what it means to belong in a galaxy that is itself constantly in motion. The more we study them, the more we realize that their mystery is not isolated to their origins. It extends to every interaction, every byproduct, every theoretical implication. These pulsars are not just ejected objects. They are revelations launched into the dark, waiting to be intercepted by minds curious enough to listen. And listen we shall. Because in the quiet rhythm of a pulsar's beat, encoded in milliseconds of magnetic precision, lies the wisdom of the stars. As we continue tracing the journey of runaway pulsars across the vast cosmic landscape, the sheer strangeness of their existence begins to blur the lines between known astrophysics and the surreal possibilities that challenge our very understanding of reality. There is something almost mythological about a star, once the blazing heart of a stellar system, being born again in violence, flung like a divine arrow into the darkness, never to return to its celestial family. But even in this seeming exile, it becomes something more, a messenger of explosive origins, a signal in the silence, a relic of a galactic heartbeat. Runaway pulsars, for all their isolation, are anything but forgotten. Their effects ripple across the electromagnetic spectrum, from radio to X-rays, from gamma rays to gravitational waves. Each signal they emit is a code: timing residuals, spin-down rates, glitches, thermal emissions, bow shocks, pulse profiles. To decode them is to peer inside the clockwork of creation. And the data is piling up. In some remarkable cases, pulsars have been observed with proper motions that allow astronomers to trace their path with exquisite precision. One such example is the pulsar PSR B1508+55, which hurtles through the Milky Way at an astounding speed of over 1,100 km per second. That's fast enough to escape the gravitational pull of the galaxy entirely. With every passing millennia, it inches further from the galactic disk, eventually bound for the deep silence of intergalactic space. The mystery behind its incredible speed has led to competing hypotheses. Was it a supernova asymmetry? A binary disruption? Or something far stranger? The truth might lie in the details of its magnetic field. Pulsars have extraordinarily strong magnetic fields, trillions of times stronger than Earth's. These fields can warp space-time, alter particle trajectories, and even affect the geometry of light. Some researchers speculate that in certain scenarios, interactions between a pulsar's magnetic field and the relativistic jets of its progenitor explosion could help channel momentum asymmetrically. In effect, the pulsar could be pushed not only by neutrino emission but also by magnetic recoil, like a cosmic railgun powered by magnetohydrodynamic violence. Even stranger still is the role of gravitational waves in this narrative. Though typically associated with massive mergers, gravitational waves are also produced by asymmetric supernovae and binary disruptions. If these events are lopsided enough to send a neutron star speeding through space, then the associated gravitational wave signals, though weak, could still be detectable with sensitive future instruments. Imagine a network of detectors like LIGO or its successors picking up ripples in spacetime from an explosion that occurred 1 million years ago, and then identifying the culprit as a runaway pulsar still hurtling through the cosmos. This would be the ultimate cosmic detective story, a whodunit that unfolds across the dimensions of time, space, and gravitation. As we think further ahead, a chilling question arises: how many runaway pulsars are out there that we haven't yet detected? Our galaxy may be teeming with these stellar nomads. Dozens, hundreds, perhaps thousands, some visible only in short bursts of radio waves, others entirely cloaked in silence. Many may no longer emit detectable radiation. These are the so-called dead neutron stars, stellar corpses that no longer spin fast enough or emit the right beams to be seen as pulsars. Yet they move, silently and relentlessly, through the void, hidden from even our most sensitive telescopes. One might be hurtling right now through the outer halo of our solar system, undetected, its presence betrayed only by the slightest gravitational tugs on passing comets or long-period asteroids. This brings us to the haunting possibility that a runaway pulsar, dead or alive, could pass dangerously close to Earth. While rare, the implications of such an encounter are profound. A rapidly rotating neutron star, even at a distance of a few light-years, could affect our solar system through its intense gravitational field or, more catastrophically, through high-energy emissions. If a pulsar were to pass within a fraction of a light-year, its beam, if aligned with Earth, could bathe the planet in X-rays and gamma rays. While the likelihood of such an event is extraordinarily low, the fact that these stars travel at hundreds to thousands of kilometers per second means that the cosmic landscape is always shifting, and we must always watch the skies. Yet for every threat they might pose, runaway pulsars offer even more promise. Their spin properties, for example, allow us to measure time with mind-bending accuracy. The best millisecond pulsars are so consistent in their timing that they rival atomic clocks. These pulsars are being used to build a galaxy-scale gravitational wave detector known as a pulsar timing array. By measuring tiny irregularities in the arrival times of pulses from a network of these cosmic lighthouses, astronomers hope to detect gravitational waves from supermassive black hole mergers and cosmic strings, events that exist far beyond the reach of LIGO. In a sense, runaway pulsars could be the key nodes in a galactic nervous system, a network through which we detect the silent tremors of the universe's most titanic collisions. Their utility as probes of spacetime is unparalleled, and their dispersion across the galaxy, thanks in part to their runaway nature, ensures that this network is widely distributed and diverse in its perspectives. No longer just relics of stellar death, these objects become instruments for mapping the fabric of reality itself. But there is one more, even deeper layer to consider: the philosophical implications. Runaway pulsars remind us that nothing in the cosmos is static. Everything moves, collides, breaks apart, and begins anew. Even the most violent events, supernovae, do not signify an end, but a transformation. A star's death is not silence, it is motion. It is radiation. It is memory cast into the vacuum. These stars that flee their birthplaces may seem tragic in their loneliness, but in fact, they are among the most communicative objects in the universe. Their pulses reach across unimaginable distances, carrying stories older than humanity, encoded in a language of light, magnetism, and gravity. We, the listeners, sit on a pale blue dot orbiting an average star, tuning in, decoding, trying to understand. And perhaps that's the most poetic truth of all, that runaway pulsars are not just speeding remnants of chaos, but cosmic storytellers. They tell of collapses, of ruptures, of separations and survivals. They remind us that exile is not the end of meaning. That movement is not absence. That to be cast into the void is not to vanish, but to endure, in rhythm, in memory, in light. We must continue to listen, to search, to chart their paths across the stars and across time itself. Because if runaway pulsars can teach us anything, it is this: in a universe that is cold and vast and often silent, the act of motion, the refusal to stay still, is the clearest sign of life. Yet even with all we've learned, the tale of runaway pulsars continues to evolve, growing richer and stranger with every new observation. These celestial vagabonds are not only moving at breakneck speeds, but they are carrying with them a time capsule of the conditions from their moment of origin. Their composition, their spin, their magnetic fields, all of it bears the fingerprints of the cataclysm that birthed them. And that makes every runaway pulsar a piece of forensic evidence in the grand crime scene of stellar death. Astronomers have begun to see these objects not just as anomalies to explain, but as tools that can map the invisible. In particular, runaway pulsars have become instrumental in helping us probe the elusive structure of the Milky Way's dark matter halo. Because these neutron stars are so dense and move at such high speeds, they interact subtly with whatever gravitational influences they pass through. That means their paths can bend ever so slightly, or their timing may drift just enough, revealing clues about the unseen mass that permeates our galaxy. Imagine this: a runaway pulsar exits the galactic disk and heads toward the halo, its trajectory meticulously tracked over decades. If dark matter clumps exist in the halo as some theories suggest, they might tug gently at the pulsar's path. Detecting even the faintest deviation could help reveal the shape and nature of dark matter distributions, something that has remained one of astrophysics' most persistent mysteries. In this way, runaway pulsars could do what no telescope alone can accomplish: map the invisible architecture of the cosmos. What's more, some scientists are beginning to wonder if certain types of runaway neutron stars might serve as natural laboratories for understanding alternative theories of gravity. General relativity has stood the test of time, but there remain anomalies at cosmic scales, places where the math doesn't quite add up without invoking dark matter or dark energy. But what if the laws of gravity themselves are subtly different under extreme conditions? A neutron star accelerating through various gravitational environments across the galactic disk and halo could experience minute effects predicted by modified gravity theories. With long-term monitoring, we might one day detect signs that hint at deeper truths beneath Einstein's elegant equations. Meanwhile, on the frontier of observational astronomy, next-generation telescopes like the Square Kilometre Array, SKA, the Vera Rubin Observatory, and the James Webb Space Telescope are poised to revolutionize how we study these elusive objects. The SKA, in particular, is expected to find tens of thousands of new pulsars, many of them with unusually high velocities or in exotic binary systems. This vast new dataset will almost certainly uncover more runaway pulsars, and perhaps some with properties that force us to rewrite our textbooks entirely. Consider the possibility of discovering a pulsar with a motion so extreme that it appears to have been ejected not just from a supernova, but from a binary system that also included a black hole or even a strange star. Or the potential of identifying runaway pulsars that originated in ancient globular clusters, having been kicked out billions of years ago and now wandering in the galactic outskirts. These detections would shed light not only on stellar evolution but on the history of our galaxy itself, how it formed, how it grew, and how its stars have scattered over time like sparks from a cosmic forge. Even now, astronomers are cataloging hypervelocity stars, objects that move so fast they can escape the Milky Way entirely. While most of these are ordinary stars, a growing number of fast-moving neutron stars are being added to the list. If confirmed, some of these hypervelocity pulsars might have originated from interactions with the supermassive black hole at the center of the galaxy, Sagittarius A. If a binary system wandered too close to this gravitational behemoth, the intense tidal forces could rip it apart, slingshotting one object into deep space while capturing the other. Such a mechanism would produce some of the fastest runaway pulsars in the universe, and tie them to one of the most extreme environments known. It's not hard to imagine, then, that our galaxy is littered with the scattered remnants of ancient stellar duels. Each runaway pulsar becomes a relic of a forgotten event, proof that even in death, stars can act with explosive drama, sending out messengers that race through space for eons. But these aren't just random messengers. Some of them are whispering secrets about the laws of physics themselves. Pulsars can undergo what are called glitches, sudden changes in their rotation rate that defy easy explanation. These events are thought to be caused by interactions between the solid crust and the superfluid core of the neutron star, or perhaps by internal rearrangements of matter under conditions we cannot replicate on Earth. When glitches occur in runaway pulsars, especially ones in isolation far from stellar companions, they allow us to isolate variables and study the glitch phenomenon in its purest form. Every glitch becomes a clue, a seismograph for a star's internal structure. And the glitching is only part of it. Pulsars can also undergo mode switching, nulling, and timing noise, all of which are changes in their signal that reveal something about the exotic quantum behavior occurring inside them. When you combine this with their high velocities, the result is like a neutron star operating as a natural particle accelerator, flinging itself through different cosmic environments, while undergoing extreme internal dynamics. These are the kinds of conditions that push the boundaries of what physics allows, and they're happening all across the sky. Even more profound is the idea that runaway pulsars may hold the key to understanding the origin of matter itself. Because neutron stars contain matter in its most compressed state, they may be the only accessible objects that harbor the conditions for exotic states like quark-gluon plasma or strange quark matter. If a runaway pulsar were to undergo a phase transition into a strange star, something that could happen spontaneously or due to interactions with interstellar matter, it might emit a unique burst of neutrinos or gravitational waves, unlike anything we've ever observed. That would be the moment we detect not just a runaway, but a transformation, a mutation in the cosmic genome that rewrites what it means to be a star. And just as we begin to comprehend these possibilities, new mysteries emerge. Some high-velocity neutron stars are curiously underluminous. Others exhibit oddly oriented magnetic fields. A few show signs of surrounding material, debris or fallback disks, that should have been blown away in the supernova but somehow remain. Are these signatures of failed explosions? Of hypernovae? Of binary mergers gone wrong? The more we study them, the more runaway pulsars seem to sit at the edge of a great transition zone, not just between life and death, but between the known and the unknown. They move through space, but they also move through conceptual boundaries, between stellar physics and quantum chromodynamics, between galactic dynamics and particle theory, between what we can observe and what we must infer. In that way, they are like us. Always moving. Always searching. Carrying with them the legacy of creation and the promise of understanding. And so the journey continues. As we push further into the cosmic frontier, another layer of fascination unfolds around runaway pulsars, their interactions with the interstellar medium, ISM, the vast expanse of gas and dust filling the spaces between stars. When a pulsar rockets through the galaxy at supersonic speeds, it creates spectacular phenomena known as bow shocks, arc-shaped waves in the ISM caused by the pulsar's wind colliding with surrounding material. These bow shocks are not only visually stunning when observed in X-ray or H-alpha wavelengths, but they also serve as laboratories for studying high-energy astrophysics. The shape, size, and brightness of these bow shocks can reveal crucial information about the pulsar's velocity, the density of the local ISM, and the geometry of its magnetic field. In some cases, they even help identify previously unknown runaway pulsars. The famous Guitar Nebula, for example, is a glowing bow shock shaped like a guitar, created by the supersonic motion of the pulsar PSR B2224+65. The nebula's shape and filamentary structure map the interaction between the pulsar wind and the surrounding medium, painting a vivid picture of how these stars sculpt their environment even as they flee. Bow shocks are not static. They evolve as the pulsar traverses different regions of the galaxy, encountering varying densities and magnetic fields. Studying these changes provides insights into the structure of the ISM and the dynamics of cosmic plasmas. Moreover, the pulsar wind itself, a flow of charged particles accelerated to near-light speeds, can energize particles in the ISM, creating cosmic rays that may eventually influence star formation processes. On a grander scale, the distribution of runaway pulsars across the galaxy contributes to the ongoing chemical enrichment of the ISM. As these neutron stars travel, they sometimes carry with them remnant material from their progenitor supernovae or generate relativistic winds that help spread heavy elements synthesized during the explosive death of massive stars. This cosmic recycling seeds the next generation of stars and planets with the raw materials for life. Yet the journey of runaway pulsars is not solely defined by their outward motion. Some pulsars born with tremendous velocity remain gravitationally bound to the Milky Way but embark on elongated orbits that take them far above and below the galactic plane. These halo pulsars provide unique perspectives on the galaxy's gravitational potential and history. By mapping their trajectories, astronomers can reconstruct past galactic events, such as interactions with satellite galaxies or dark matter subhalos that may have perturbed their paths. The kinematic data gleaned from these pulsars also help refine models of the Milky Way's mass distribution, which is notoriously difficult to pin down. This has far-reaching implications, including our understanding of dark matter's role in galaxy formation and evolution. Each runaway pulsar thus becomes a dynamic probe, tracing the invisible scaffolding that holds our cosmic neighborhood together. In a stunning convergence of theory and observation, some runaway pulsars may even play a role in explaining mysterious high-energy phenomena observed near the edges of the galaxy or in intergalactic space. Fast-moving neutron stars with intense magnetic fields are potential sources of fast radio bursts, FRBs, brief, powerful flashes of radio waves that last only milliseconds but release enormous amounts of energy. While the origin of FRBs remains one of astrophysics' hottest mysteries, runaway pulsars are a promising candidate population. Their rapid motion through varied environments could trigger mechanisms for such bursts, whether through magnetic reconnection events, crustal fractures, or interactions with surrounding plasma. If confirmed, this connection would link two of the universe's most enigmatic phenomena, the runaway pulsar, a star ejected into cosmic exile, and the fast radio burst, a fleeting signal from the depths of space. It would underscore how even the most transient signals can be tied to the enduring journeys of ancient stellar remnants. Looking even further ahead, the concept of runaway pulsars invites speculation about their role in the broader cosmic ecosystem. In the vast voids between galaxies, there may exist intergalactic pulsars, neutron stars that have escaped the gravitational grip of any galaxy entirely. Such objects would be profoundly isolated, drifting alone through near-perfect vacuum. Their faint signals might be the faintest whispers in the cosmic dark, yet their detection could open a new window on galaxy formation, gravitational interactions, and the large-scale structure of the universe. Detecting intergalactic pulsars poses enormous challenges. Their signals would be greatly weakened by distance, and their isolation means they would lack the environmental cues often used to identify galactic pulsars. However, future instruments and surveys designed for extreme sensitivity could one day uncover these cosmic wanderers, illuminating the ultimate fate of runaway stars. On a more speculative front, the study of runaway pulsars also touches on the question of cosmic acceleration and velocity distribution in the universe. Some researchers wonder whether the velocities of neutron stars could provide clues about anisotropies or preferred directions in the cosmos, testing cosmological principles like isotropy and homogeneity on smaller scales. Although such ideas remain fringe, they demonstrate how studying objects as specific as runaway pulsars can ripple outward into the grandest questions of cosmology. The saga of runaway pulsars is emblematic of modern astrophysics itself, a blend of observation, theory, and imagination. These stars are not just remnants of explosive deaths, they are living laboratories, probes of fundamental physics, markers of galactic history, and perhaps even keys to unlocking universal mysteries. Their journeys remind us that in the vast theater of the cosmos, every object has a story, every movement matters, and the search for understanding is unending. Runaway pulsars challenge us to look beyond the static night sky and embrace a universe in motion, filled with wonders both terrifying and sublime. They beckon us to listen closely to the rhythm of the stars, to decode their ancient pulses, and to marvel at the cosmic dance that has been unfolding for billions of years, a dance in which even the most isolated traveler has a vital role. As we delve deeper into the enigma of runaway pulsars, another intriguing dimension emerges: their role as natural cosmic clocks and precision laboratories for testing the very fabric of spacetime. Pulsars, due to their incredibly stable rotation periods, have long been used as astronomical timekeepers with astonishing accuracy. When these stellar remnants are propelled at high velocities through the galaxy, their precise timing signals become invaluable tools for probing gravitational phenomena and testing the predictions of Einstein's general relativity under extreme conditions. In particular, runaway pulsars offer a unique advantage. Their high speeds and solitary nature minimize perturbations from companion stars or complex environments. This isolation allows astronomers to detect subtle influences, such as the gravitational pull of passing dark matter clumps or the slight warping of spacetime caused by massive objects. By monitoring the arrival times of pulses over years and decades, researchers can hunt for tiny anomalies that might hint at the presence of otherwise invisible matter or reveal the influence of gravitational waves rippling through the galaxy. One of the most groundbreaking prospects in astrophysics is the use of pulsar timing arrays (PDAs), networks of pulsars scattered across the sky, to detect low-frequency gravitational waves, ripples in spacetime generated by cataclysmic events like merging supermassive black holes. Runaway pulsars, especially those with well-measured distances and velocities, enrich these arrays by filling in gaps in the galactic coverage and increasing sensitivity. Their rapid motion through varying gravitational potentials means their pulse arrival times may carry unique signatures, enhancing the detection capability of PDAs. Moreover, studying the timing irregularities of high-velocity pulsars helps scientists better understand intrinsic pulsar behaviors, such as sudden spin-ups known as glitches or slowdowns called timing noise, which are linked to the complex physics inside neutron stars. Since runaway pulsars are often far from crowded stellar environments, disentangling these internal phenomena from external gravitational influences becomes more straightforward. This clarity advances neutron star physics and informs models of superfluidity, crust dynamics, and magnetic field evolution. Beyond timing, runaway pulsars also captivate astronomers through their emission mechanisms. Pulsars emit beams of radiation across the electromagnetic spectrum, from radio waves to gamma rays, powered by their intense magnetic fields and rapid rotation. When propelled through diverse interstellar environments at breakneck speeds, these emission characteristics can vary dramatically. For instance, the interaction between a pulsar's magnetosphere and surrounding plasma can alter the shape, intensity, and polarization of emitted radiation. Such variability offers clues to the particle acceleration processes and magnetic reconnection events occurring in these extreme environments. It also sheds light on the pulsar wind nebulae that sometimes trail behind runaway pulsars, glowing in X-ray and radio wavelengths. These nebulae are cosmic laboratories where relativistic particles collide with interstellar matter, producing synchrotron radiation and high-energy emissions that reveal the physical conditions and dynamics of the pulsar's surroundings. Runaway pulsars have also challenged our understanding of binary evolution. Traditionally, neutron stars were thought to gain their velocity kicks during asymmetric supernova explosions. However, recent studies suggest that some pulsars may achieve their extreme speeds through complex interactions in binary or even triple star systems, where gravitational slingshots and mass exchanges propel them outward. These scenarios complicate the picture of stellar death and birth, suggesting that runaway pulsars are survivors of chaotic stellar dances rather than solitary explosion aftermaths. Adding to this complexity are the peculiar cases of pulsars exhibiting extreme velocities alongside unusual spin rates or magnetic fields. Some are found to be millisecond pulsars that have been spun up by accreting matter from companions before being ejected, while others show magnetic fields billions of times stronger than typical pulsars. These extremes hint at a spectrum of evolutionary pathways and explosive histories, with runaway pulsars occupying a diverse and dynamic niche. In the cosmic scale of things, runaway pulsars remind us of the interconnectedness of processes, stellar evolution, gravitational dynamics, quantum matter, and galactic ecology. Each pulsar's journey is a thread in the vast tapestry of the universe, weaving together phenomena from the smallest scales of neutron star interiors to the grandest architectures of galaxies. Even as we peer into the depths of space with ever more powerful instruments and simulations, runaway pulsars stand as enigmatic emissaries, pushing us to refine our theories and expand our imaginations. They compel us to ask fundamental questions about matter, energy, and the forces that shape the cosmos. And in doing so, they ignite the eternal human quest for knowledge, a journey as boundless as the stars themselves. Peering beyond the immediate astrophysical phenomena, runaway pulsars also provoke fascinating questions about their potential role in the broader context of cosmic evolution and even the search for extraterrestrial intelligence. While these neutron stars are typically considered remnants of stellar death, their extraordinary energy outputs and extreme environments invite speculation about whether they could serve as natural beacons or obstacles in the cosmic landscape. Given their stable pulsations and immense energy emissions, some theorists have pondered whether advanced civilizations might harness pulsars as natural lighthouses for interstellar navigation or communication. The concept, though speculative, is grounded in the fact that pulsars are among the most reliable cosmic clocks known and can be detected across vast distances. Runaway pulsars, with their high velocities and changing positions, could theoretically provide moving reference points or convey dynamic information, if such civilizations existed and had the technological prowess to modulate or utilize these signals. From a more scientific standpoint, pulsar signals have already been proposed as galactic GPS markers for future interstellar travelers, given their precise timing and ubiquity. Runaway pulsars, traversing different regions of the galaxy and even escaping it, expand the spatial range of these cosmic signposts. This idea gains particular interest with the growing enthusiasm for interstellar probes and deep space navigation, suggesting that understanding the distribution and trajectories of runaway pulsars could aid humanity's future journeys beyond the solar system. Moreover, the magnetic fields and relativistic particle winds emitted by runaway pulsars influence the habitability of nearby regions. Intense radiation and energetic particles can strip atmospheres, disrupt biological molecules, and create hazardous environments for life as we know it. Thus, the paths of these high-velocity neutron stars may delineate safe zones and danger zones within the galaxy, shaping where life might persist or arise. Mapping the trajectories of known runaway pulsars becomes crucial not only for understanding stellar dynamics, but also for assessing the galactic habitability landscape. At a more fundamental level, runaway pulsars challenge our understanding of matter under extreme conditions. Inside these stars, matter is compressed to densities exceeding atomic nuclei, forming an exotic state that defies terrestrial replication. Theories predict that cores of neutron stars might contain strange quark matter, where up-down, and strange quarks flow freely in a superdense soup. Confirming the existence of such exotic phases would revolutionize nuclear physics and deepen our grasp of quantum chromodynamics. Runaway pulsars provide a unique opportunity to study these phases because their isolated nature and sometimes extreme spin rates offer cleaner observational signatures. For example, sudden changes in rotation, glitches, may be connected to phase transitions inside the star's core, hinting at the internal composition. Observing these events in high-velocity pulsars, far from interfering sources, allows astrophysicists to better constrain models of neutron star interiors and the state of matter at supernuclear densities. In tandem with observational astronomy, numerical simulations have become a vital tool for exploring runaway pulsars. Cutting-edge computer models simulate the complex physics of asymmetric supernova explosions, the resulting neutron star kicks, and the subsequent motion of these stars through galactic potentials. These simulations incorporate magnetohydrodynamics, nuclear reactions, and relativistic effects, striving to replicate the incredible diversity of observed pulsar velocities and spin properties. Remarkably, these models have revealed that subtle asymmetries in neutrino emission during the supernova can impart significant kicks to newborn neutron stars, one of the leading explanations for runaway pulsars' velocities. Neutrinos, elusive particles that flood the universe, carry away vast amounts of energy during a star's collapse. If their emission is uneven, it can act like a rocket thrust, sending the neutron star speeding through space. This neutrino-driven kick mechanism remains an active area of research, with ongoing experiments like the IceCube Neutrino Observatory providing insights into neutrino behavior that may eventually illuminate these processes. Furthermore, the discovery of pulsars moving at speeds exceeding 1,000 km per second, nearly 3 million km per hour, pushes the boundaries of known physics. How can a star so dense and massive accelerate to such velocities without being torn apart? This puzzle challenges models of supernova dynamics, binary star interactions, and even suggests the possibility of entirely new astrophysical phenomena. Another aspect capturing scientists' attention is the apparent correlation between pulsar velocity and magnetic field strength. Some studies suggest that pulsars with higher kicks also have stronger magnetic fields, indicating that the explosion asymmetry and magnetic field amplification processes may be linked. This correlation could reveal deeper connections between a star's magnetic evolution and the physics of its final moments. On the observational frontier, missions such as NASA's Neutron Star Interior Composition Explorer, NICER, and the European Space Agency's upcoming Athena X-ray Observatory aim to provide unprecedented detail on neutron star properties. These instruments will measure pulsar sizes, masses, and surface compositions, refining our understanding of their internal structure. When combined with precise velocity measurements from radio telescopes, this data will help decode the life stories of runaway pulsars, how they formed, how they moved, and how they evolved. As humanity extends its reach into space, the study of runaway pulsars stands as a reminder of the cosmos' dynamism and complexity. These celestial travelers are far more than remnants of explosive deaths. They are vital actors in the ongoing saga of cosmic evolution, laboratories for fundamental physics, and signposts guiding our journey into the unknown. The mystery of runaway pulsars is far from solved. With each new discovery, new questions arise, propelling us toward deeper understanding and fresh wonder. They beckon us to continue exploring, to keep listening to the faint, rhythmic pulses that echo across the void, and to embrace the vast, moving story of our universe. The journey of runaway pulsars through the galaxy also provides a remarkable lens through which we can examine the life cycle of stars on a cosmic scale. Each runaway pulsar is a remnant of a colossal event, a supernova explosion that not only ends the life of a massive star but also shapes the destiny of everything around it. These explosions are the engines of chemical enrichment in the universe, forging elements heavier than iron and scattering them into the interstellar medium. A runaway pulsar, then, is not just a traveler, it is a survivor, a fragment of stellar violence propelled into the vastness of space, carrying with it the fingerprints of the processes that created the building blocks of planets, and ultimately, life. Over millions of years, these pulsars trace long, looping trajectories through the galaxy, sometimes passing through spiral arms, dense molecular clouds, and even halo regions far above the galactic disk. In doing so, they interact with a variety of environments, each encounter altering their motion slightly, sculpting their nebulae differently, and influencing the emissions we observe from Earth. As they travel, they may even pass near other stars or planetary systems, their intense radiation and magnetic fields potentially disrupting the formation of planets or altering the chemistry of protoplanetary disks. Interestingly, the high speeds of some runaway pulsars mean they are likely to escape the Milky Way altogether, especially if they receive a powerful enough kick during their birth. Once outside the galaxy, they enter the vast, cold, and lonely void of intergalactic space, a place so empty that even light from the nearest stars can take thousands or millions of years to arrive. Out there, a neutron star may travel undetected for eons, its pulses continuing in isolation, invisible to our instruments until technology or fortune allows us to glimpse it again. These intergalactic wanderers may be among the loneliest objects in the cosmos, their silence a testament to the immensity of space. Yet even in their silence, they teach us. Each measurement of a runaway pulsar's position, velocity, and timing contributes to a growing catalog of knowledge, a data set that stretches across decades and continues to refine our models of stellar death, galactic evolution, and cosmic dynamics. This is especially important in a universe that is itself in motion, expanding, shifting, and changing with time. Understanding how neutron stars move helps us reverse engineer the past, reconstructing where stars exploded, how the galaxy has shifted, and what forces have shaped its spiral arms and star-forming regions. Furthermore, the sheer variety of observed runaway pulsars challenges our preconceptions. Some spin hundreds of times per second, appearing as millisecond pulsars. Others rotate more slowly, with powerful magnetospheres emitting beams of radiation in the X-ray and gamma-ray bands. Some are radio-loud, easily detectable by ground-based observatories, while others are radio-quiet, only visible in high-energy wavelengths. Each one offers a slightly different puzzle. Why was it born the way it was? What caused its unique characteristics? And how does its journey relate to the broader cosmic web? For scientists, runaway pulsars are also tools to investigate gravitational interactions in multiple star systems. When a massive star explodes in a binary or triple system, the dynamics can be complex. If the supernova ejects the neutron star fast enough, it might leave behind its companion or take it along in a high-speed binary, creating a so-called runaway binary pulsar. In extremely rare cases, the system may remain bound, orbiting rapidly as it escapes the galaxy. The gravitational interplay in these situations allows astrophysicists to model three-body problems under real-world conditions, something notoriously difficult even with modern computing power. Some of the fastest known pulsars provide compelling evidence for these exotic origins. Pulsar B1508+55, for instance, travels at over 1,000 km per second and shows no evidence of a companion, suggesting a powerful asymmetric kick at birth. Others, like Pulsar J0002+6216, have left trails in the interstellar medium that point directly back to their supernova remnants, letting us trace their journeys with eerie precision. These trails are not only beautiful, they are relics of motion, etched across light years of space, giving us visual testimony to the forces that launched them. In recent years, machine learning and AI have become indispensable tools in identifying and analyzing pulsars, especially those with unusual trajectories or weak signals. Surveys like those conducted with the Square Kilometre Array pathfinders and the Fermi Gamma Ray Space Telescope produce vast amounts of data, far too much for humans to sift through unaided. Algorithms trained on known pulsar signatures can now flag likely candidates with incredible efficiency, speeding up discoveries and uncovering exotic cases that challenge our models. As these technologies improve, we may discover classes of neutron stars that we have never seen before, perhaps substellar remnants that barely qualify as pulsars, or exotic compact objects born in ways we have yet to understand. Runaway pulsars may turn out to be not just travelers, but the harbingers of entire undiscovered populations of stellar remnants, hidden in the farthest reaches of the galaxy or even beyond. And then there is the philosophical dimension. Runaway pulsars, hurtling through space at unthinkable speeds, completely alone, are metaphors for isolation and endurance. They are cosmic orphans, launched into the dark with no destination, no return. Yet they endure. Their pulses continue, beating like the heart of a lost traveler, steady, unwavering, measurable. In their persistence, there is a strange kind of hope. A reminder that even in the vast, cold emptiness of the universe, something can continue to move, to shine, to speak. They speak in pulses, not in words. But if we listen closely, they tell us stories of cataclysm and survival, of motion and memory, of distance and discovery. They speak of the violence that created them and the silence that follows. They tell us that the universe is not static, not still, but alive with motion, bursting with energy, filled with the echoes of ancient deaths that have become beacons in the night. The search for these runaway stars continues. With each new detection, we sharpen our picture of the cosmos. With each pulse recorded, we time the beating heart of the universe itself. With each journey mapped, we trace the pathways that stars take when they are set free. And so we look upward and outward, listening to the rhythm of the sky, following the trails of those who have left their homes behind and ventured into the unknown. The story of runaway pulsars is not just about stars. It is about motion, about resilience, about the infinite pathways that lie ahead. Their stories are not confined to their motion alone. They stretch into the very core of cosmic origins, linking runaway pulsars to the formation and evolution of the Milky Way itself. As these stellar remnants traverse vast galactic distances, they serve as tracers of the gravitational potential of the galaxy. By mapping their trajectories, scientists gain insights into the distribution of both visible and dark matter that exerts gravitational influence across the galactic disk and halo. Since runaway pulsars often move far beyond the plane of the Milky Way, they offer a rare opportunity to probe the otherwise invisible structure of the galactic halo, an immense region filled with dark matter and ancient stars. This has profound implications. If we can model the paths of runaway pulsars with high precision, we can begin to estimate the gravitational landscape through which they pass. Discrepancies between predicted and observed paths could suggest areas of dense, unseen mass, potential dark matter clumps that don't emit or reflect light but exert real gravitational force. In this way, runaway pulsars act like pinballs in a cosmic machine, their bouncing and bending giving away the hidden machinery of the galaxy. One particularly promising method is to examine the shadows, or wake effects runaway pulsars create in the interstellar medium. As these neutron stars blast through space at supersonic speeds, they compress gas and dust ahead of them and leave behind a turbulent wake. These bow shocks and trailing tails, often observed in infrared and X-ray wavelengths, carry embedded information about the pulsar's velocity, the density of the medium it's plowing through, and even the magnetic fields of the region. Bow shocks are not merely beautiful structures. They are forensic trails left by ancient stellar cataclysms, full of clues waiting to be deciphered. Perhaps even more intriguingly, there are rare cases in which pulsars are ejected not by supernovae, but possibly by interactions with the supermassive black hole at the center of the Milky Way. Theoretically, if a binary star system ventures too close to the galactic center, the intense gravitational forces from the central black hole, Sagittarius A, can rip the system apart. One star may be captured into a tight orbit or consumed, while the other is flung outward at extraordinary speeds, possibly as a neutron star if a previous supernova had occurred. Such a mechanism, while rare, could account for some of the fastest runaway pulsars detected. These stars, accelerated by a cosmic slingshot effect, may be racing away from the galactic core at speeds sufficient to escape the Milky Way entirely. If confirmed, this would not only underscore the dynamic influence of the central black hole but also offer direct observational proof of one of the most extreme gravitational interactions in nature. Runaway pulsars also provoke a re-evaluation of star formation and death rates across the galaxy. For every one that we detect, there are likely many more we've missed, those obscured by dust, moving through quiet regions of space, or simply beyond the reach of our instruments. This suggests that the galactic population of neutron stars may be vastly underestimated. And because neutron stars are crucial endpoints in the life cycles of massive stars, they serve as a statistical backbone for understanding stellar demographics on a cosmic scale. Furthermore, the kinematics of runaway pulsars can shed light on the nature of supernova asymmetries. Supernovae were once thought to be mostly spherical explosions, but the kicks imparted to neutron stars suggest otherwise. These asymmetries might be the result of intense convection during core collapse, magnetic field interactions, or directional neutrino emissions. Each mechanism carries its own unique fingerprint in the final speed, spin, and trajectory of the resulting pulsar. Runaway pulsars help decode these fingerprints. Their velocities and spin alignments may betray the angle of explosion asymmetry or indicate whether the birth explosion was accompanied by a gamma-ray burst or jet. Some high-velocity neutron stars may have been born in hypernovae, supercharged explosions tied to the deaths of the most massive stars in the universe. Understanding the relationship between runaway velocities and the type of supernovae enriches our comprehension of stellar death and contributes to refining simulations of core collapse events. The chemical trail left behind by runaway pulsars also informs galactic chemical evolution. A neutron star racing through the interstellar medium may encounter pockets of gas and dust left by other dead stars. Over time, these interactions stir and mix the materials, contributing to the redistribution of elements necessary for new star formation. In this way, runaway pulsars don't just mark endings, they indirectly sow the seeds of new beginnings. One might also consider the theoretical upper limits. Could there be neutron stars moving even faster than what we've observed, so fast that their origins cannot be explained by known physics? If one were to detect a pulsar with an unreasonably high velocity, it might force us to consider entirely new physics, unknown forms of gravitational interaction, the presence of exotic matter, or even hypothetical interactions with dark energy. Some scientists have even proposed that certain pulsars, if moving fast enough, might hint at phenomena outside the standard model of particle physics, inviting speculation about fifth forces, mirror matter, or the long-sought unification of gravity with quantum mechanics. Despite all these advances, one of the most powerful aspects of studying runaway pulsars is their longevity. While other cosmic phenomena like supernovae, gamma-ray bursts, or tidal disruption events are brief and fleeting, pulsars endure. Their lighthouses shine for millions of years. This temporal persistence allows long-term study across generations of astronomers, offering a consistent point of reference that is rare in a universe of impermanence. The heartbeat of a pulsar, measured in fractions of a second, is the echo of an ancient death cry. It repeats, unchanging, through epochs of cosmic time. And when that heartbeat is moving across the galaxy at thousands of kilometers per second, it carries not just radiation but also a story, of birth and fire, of expulsion, of a lonely journey that continues even now, as we listen. These cosmic vagabonds show us that the universe is in motion, that destruction can lead to endurance, and that every star, no matter how alone, contributes something essential to the grand celestial dance. In their motion, they reflect our own desire to explore, to move beyond boundaries, to seek understanding not just in what is near, but in what is far. And perhaps one day, in some distant future, a spacecraft will pass close to a runaway pulsar, listening to its pulses like a song written by the universe itself, ancient, steady, and true. What makes the study of runaway pulsars even more compelling is the mysterious and often serendipitous nature of their discovery. Some have been found purely by accident, detected when astronomers were studying unrelated regions of space or while conducting broad-scope surveys not specifically targeting pulsars. These accidental encounters highlight just how many remain hidden, cloaked in the obscurity of the galactic halo or masked by the interference of cosmic dust. Every new detection not only deepens our understanding but also widens the scope of possibility, inviting the thrilling question: how many more of these cosmic wanderers are out there, unseen and untracked? In recent years, astronomers have begun piecing together pulsar motion histories using highly sophisticated tools like the Very Long Baseline Array, VLBA, the Chandra X-ray Observatory, and ESA's Gaia mission. Gaia, in particular, has revolutionized our ability to pinpoint proper motions and distances of stars with astonishing accuracy. By combining Gaia's astrometric data with pulsar timing information from radio telescopes, scientists can reconstruct the three-dimensional motion of these objects, essentially tracing their steps backward through the galaxy. This enables researchers to locate their points of origin, often within ancient and long-dissipated supernova remnants, allowing for precise age estimations and explosion modeling. One spectacular case involves Pulsar PSR J0002 plus 6216, which has a bow shock stretching for 13 light-years, clearly indicating its movement through the interstellar medium. Its trajectory points directly back to a known supernova remnant, CTB1, providing irrefutable proof of its origin and runaway nature. This is more than just an interesting anecdote, it's a scientific Rosetta Stone. It allows astrophysicists to verify their models about how supernova explosions impart kinetic energy, how remnants evolve over tens of thousands of years, and how the resulting pulsar behaves over immense distances. Furthermore, the interaction of runaway pulsars with the galactic environment can spark unexpected physical phenomena. When a fast-moving neutron star cuts through dense regions of the interstellar medium, it can trigger compression waves that may initiate star formation in molecular clouds. This introduces a tantalizing possibility that the death of a star, far from being an endpoint, may actually catalyze the birth of others, not just in the vicinity of the supernova, but potentially light-years away along the pulsar's path. These feedback mechanisms represent a cosmic chain reaction, one death setting off a cascade of creation stretching across the galaxy. But not all pulsars behave according to the rules we expect. There are the so-called intermittent pulsars, which switch their emissions on and off without a clear pattern. Some may vanish from radio observability for months or years before reappearing. When such objects are runaway pulsars, the mystery deepens. Is their variability due to intrinsic magnetic field shifts, or are they interacting with different kinds of interstellar material along their journey, disrupting or enhancing the beam we receive? The question remains open and continues to push the limits of pulsar physics. Adding even more complexity are magnetars, neutron stars with magnetic fields 1,000 times stronger than those of typical pulsars. Though not all magnetars are runaway, those that are present some of the most extreme conditions in the known universe. Their magnetic fields can distort atoms into needle-like shapes and unleash massive X-ray flares capable of disrupting satellites and affecting Earth's magnetosphere, even from thousands of light-years away. If such a magnetar were also a runaway, it would effectively become a high-speed cosmic flamethrower, its radiation slicing through the galaxy like a torch through fog. And as if nature hadn't already given us enough to contemplate, theoretical astrophysicists have proposed even more exotic versions of neutron stars, such as quark stars or preon stars, which might also be born in supernovae and ejected as runaways. Though these objects remain hypothetical, their possible existence adds a layer of speculative wonder to the pursuit of pulsars. If any of the known runaway pulsars exhibit anomalies in mass, spin, temperature, or emission profiles, they might be candidates for one of these even stranger types of compact stars. Their identification could rewrite our entire understanding of matter at nuclear densities. We must also consider the relativistic implications of pulsars moving at such incredible speeds. At velocities exceeding hundreds of kilometers per second, time dilation becomes noticeable, albeit slight. These effects must be accounted for in high-precision pulsar timing models, particularly in binary systems where gravitational interactions are already extreme. The movement through varying gravitational fields also affects how their signals reach us, a factor crucial in the application of pulsars as precise cosmic clocks and navigational beacons. This brings us to one of the most revolutionary applications of pulsars, interstellar navigation. Pulsars, especially millisecond pulsars, are so consistent that they rival atomic clocks in timing accuracy. The idea of using them as cosmic GPS signals for spacecraft is no longer science fiction. NASA's Sextant project has already demonstrated autonomous X-ray navigation using pulsar signals. Now imagine the added benefits of understanding runaway pulsars in this context. As these objects migrate to the galaxy's outer edges, or beyond, they become new waypoints in the celestial coordinate grid, extending our navigation network across the void. A future spacecraft venturing beyond the heliopause could lock onto a known runaway pulsar for orientation, essentially navigating by the echoes of ancient stellar deaths. Their contribution to gravitational wave science is equally significant. When runaway pulsars form binary systems, especially with white dwarfs or other neutron stars, they become sources of gravitational waves detectable by facilities like LIGO and Virgo. The orbital decay of these systems, as predicted by general relativity, offers a pristine testing ground for Einstein's theory. Some of these binaries might eventually merge, resulting in kilonovae that release heavy elements and further gravitational waves, enriching both our telescopes and detectors with new forms of data. From the philosophical to the practical, the scientific to the speculative, runaway pulsars are a nexus of inquiry and imagination. They touch on nearly every branch of astrophysics: stellar evolution, supernova mechanics, galactic dynamics, interstellar chemistry, quantum physics, relativistic mechanics, and even the future of space travel. And yet, despite all we've uncovered, the majority of their stories remain untold. Our instruments can only observe a fraction of the sky at any given time. Our sensitivity is limited by interference, technology, and funding. But the universe is not waiting. Even now, countless pulsars move silently across the heavens, their paths unmeasured, their pulses unheard. They are ghostly runners on a cosmic track, each carrying with it a message from the depths of time. We have only just begun to listen. As our instruments grow more sensitive and our observational techniques more refined, we stand at the threshold of a new era, an age in which even the most remote runaway pulsars may one day be discovered, catalogued, and studied in astonishing detail. The future of astronomy, particularly radio and X-ray astronomy, is inexorably tied to what these elusive travelers can reveal. One of the most ambitious projects on the horizon is the Square Kilometre Array, SKA, a next-generation radio telescope array being built in Australia and South Africa. When completed, it will be the largest radio telescope in the world, capable of detecting incredibly faint signals from deep space, including the faint heartbeats of the most distant and dim runaway pulsars. The SKA promises to revolutionize our understanding of the pulsar population as a whole, potentially increasing known pulsar detections by an order of magnitude. And among those detections will likely be hundreds, if not thousands, of pulsars that are not merely stationary, but racing across the galaxy with the telltale signatures of runaway behavior. With better precision and longer observation windows, the velocity, direction, timing, and even polarization data from these objects can be collected and modeled with far more accuracy than ever before. Imagine a future database, not just of star charts or black hole candidates, but of active, migrating neutron stars catalogued in real time. Each entry would include origin coordinates, projected trajectory, estimated age, current speed, and beam profile data. Such a record would not only offer a dynamic map of the galaxy's evolutionary processes, but also serve as a live log of its most extreme survivors. Future missions could rely on this registry not only for scientific inquiry, but also for deep space travel, orientation, and even gravitational lensing studies. It's also worth noting the potential implications of runaway pulsars in the realm of theoretical cosmology. Some physicists speculate that these fast-moving remnants may cross boundaries of gravitational fields we have yet to properly define, possibly acting as test masses for detecting the elusive curvature effects of large-scale cosmic structures. Could a runaway pulsar, moving at extraordinary speeds, act like a probe into the intergalactic medium itself? Might its deviation from predicted paths reveal weak gravitational lensing by massive, dark halos or even interactions with the cosmic web? Moreover, as our understanding of high-energy astrophysics deepens, we've begun to consider the connection between runaway pulsars and cosmic rays. These fast-moving neutron stars, particularly magnetars and those with relativistic wind nebulae, may contribute to the sea of high-energy particles that constantly bombard Earth. If these runaway pulsars are accelerating particles to near-light speeds and ejecting them into space, then they may be one of several contributors to the cosmic ray background, a mystery that has puzzled scientists for decades. Mapping pulsar paths in conjunction with cosmic ray detections could eventually lead us to their point sources. Some theories even push this further. There is speculation that certain unusually energetic pulsars could produce or interact with exotic particles, axions or sterile neutrinos, for example, that are predicted by extensions of the Standard Model. If confirmed, this would transform runaway pulsars from mere astrophysical curiosities into active laboratories for particle physics, operating in regimes of energy and density we could never replicate on Earth. In this way, they might help bridge the gap between the cosmos and the quantum, between the infinite vastness of space and the infinitesimal complexities of subatomic structure. Even in the realm of SETI, the search for extraterrestrial intelligence, runaway pulsars offer a strange kind of hope. Their precise and predictable pulses, emitted with regularity that rivals atomic clocks, make them excellent natural beacons. It is not entirely unreasonable to imagine that an advanced civilization might harness or mimic these signals for communication or navigation. A runaway pulsar, with its distinct high-velocity signature and unique emissions, could be used like a cosmic waypoint, a signpost across the stars. If such a civilization were monitoring pulsars, or even using them to power or direct spacecraft via gravitational assist or beam navigation, our understanding of them would suddenly leap from the astrophysical to the interstellar. There are also lingering mysteries that defy explanation. In some regions of the sky, runaway pulsars have been found in strange isolation, far from the known supernova remnants, without obvious companions, and without discernible origin points. How did they come to be there? Were their progenitor systems lost to time, or is it possible we're missing a whole class of formation mechanisms? Could some neutron stars be born in unusual, low-luminosity supernovae that leave behind almost no visible trace? Or perhaps, though still speculative, are there non-supernova events capable of creating neutron stars and hurling them into space? Runaway pulsars may also offer clues about the final fate of our galaxy. As the Milky Way begins its long, slow collision and merger with the Andromeda Galaxy over the next several billion years, gravitational interactions will reshape the galactic structure entirely. Simulations predict that many stars, and by extension many pulsars, will be ejected from the resulting galactic system during this colossal event. By studying the current population of runaway pulsars, especially those on hyperbolic orbits, we can begin to model what that future distribution may look like. It's a strange but beautiful thought, that the runaway pulsars of today are a preview of the gravitational ballet that will one day fling stars like fireworks into intergalactic space. And still, despite all the data, despite the growing catalogs, despite the powerful telescopes and the refined algorithms, these objects retain their mystery. Every pulse they emit is both a data point and a poem, a coded whisper from a star that died long ago, a whisper that continues to travel through space, crossing parsecs, echoing in the void. These whispers speak of violence, of isolation, of resilience, of motion, and above all, of time. To study runaway pulsars is to stand at the intersection of the past and the future, to read a story written in gravity, radiation, and motion. It is to recognize that even in death, a star can move with purpose. That even in solitude, it can leave a trail. That even in silence, it can speak. And maybe that's what draws us to them. Not just the science, not just the mechanics, but the symbolism. They are the exiled kings of the cosmos, stripped of mass and throne, yet hurtling ever forward. They are the mythic wanderers, the galactic Odysseuses, carrying tales from the heart of creation. And they do not stop. As we reach deeper into this ever-unfolding mystery of runaway pulsars, the story continues to evolve, not linearly, but as an expanding sphere of ideas, each facet revealing new complexity, new wonder, and new possibilities. And one of the most remarkable aspects of studying these objects is how frequently they subvert expectations. Just when astronomers believe they have mapped the boundaries of known pulsar behavior, a new discovery emerges that flips the entire understanding upside down. This is the nature of runaway pulsars, not just to escape their physical place of origin, but to constantly flee the limits of what we think we know. Take, for instance, the strange rotational behaviors exhibited by some runaway pulsars. While most neutron stars slow down predictably over time due to magnetic braking, some have been observed to experience sudden speed-ups, known as glitches. These glitches are thought to result from interactions within the neutron star's superfluid interior, a bizarre state of matter where viscosity effectively disappears and quantum effects dominate. In runaway pulsars, glitches can also interact with the pulsar's high velocity in surprising ways. For example, a glitch might temporarily alter the shape or direction of the pulsar's beam, creating observational confusion on Earth where the pulsar may appear to vanish, only to reappear later from a slightly shifted perspective. The physics inside these stars is not just extreme, it's arguably unknowable by traditional experimentation. Neutron stars are essentially cosmic pressure cookers, compressing mass with such force that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Inside, neutrons are packed so densely that their quantum states begin to overlap, forming what's sometimes called neutron degenerate matter. In runaway pulsars, where the added kinetic energy may influence internal dynamics in ways not seen in stationary stars, we gain a unique observational window into this ultra-dense realm of physics. Some researchers have proposed that the extreme environments within these rapidly moving pulsars could also give rise to even more exotic forms of matter. Could strange quark matter, composed of up, down, and possibly strange quarks, be lurking in the cores of some of the fastest runaway pulsars? These theoretical, strange stars might have properties radically different from those of conventional neutron stars, such as altered cooling rates, different glitch behaviors, or unique gamma-ray signatures. If such stars exist, finding them among the known population of runaway pulsars might be our best chance to detect them. And then there's the question of what lies beyond the edge of the galaxy. When a runaway pulsar achieves escape velocity, a speed exceeding roughly 550 km per second, it can leave the gravitational grasp of the Milky Way entirely. These hypervelocity pulsars, once ejected, enter intergalactic space, an ocean of near-perfect vacuum populated only by tenuous wisps of gas and the dark matter scaffolding of the universe. In such an environment, stripped of interference from dense stellar neighborhoods, these pulsars become remarkably clean astrophysical laboratories. There's profound irony in this. The further they get from the galactic center, from stars, from planets, from everything we know, the more clearly their signals might arrive at Earth. Freed from the electromagnetic clutter of the galaxy, their beams can propagate across cosmic distances with minimal distortion. Detecting and studying these galactic exiles gives us not only data about their own nature but also information about the intergalactic medium they traverse, its density, composition, and magnetic fields. These hypervelocity pulsars might even be our messengers across the cosmic web. If humanity ever develops interstellar or intergalactic probes, or if we ever build instruments on moons orbiting distant stars, runaway pulsars could serve as the ultimate lighthouses. Their unwavering pulses could help us triangulate position with unimaginable precision, navigating us across distances so vast that current space travel ambitions seem quaint by comparison. In speculative scenarios, it's even been suggested that civilizations more advanced than ours might already be doing this. What if runaway pulsars are more than mere remnants of stellar death? What if they are tools, used, monitored, or even redirected by advanced technological beings to mark territories, send signals, or guide machines? While purely hypothetical, these ideas serve to remind us that in the vast silence of the universe, even the most inert-seeming object can carry profound meaning. A pulsar is not just a corpse, it is a storyteller, and in its movement, a mapmaker of cosmic histories. There's also a philosophical allure to runaway pulsars. In their flight, we see echoes of universal entropy, the drive toward dispersal, toward spreading energy, toward the infinite. A pulsar doesn't seek the edge of the galaxy, but it heads there regardless, propelled by chaos and sealed fate. It is both a record of violence and a symbol of survival, burning on long after its own creation has crumbled to dust. This dichotomy, destruction giving way to near-eternal persistence, is what makes pulsars so compelling to the human imagination. They embody our most paradoxical instincts, to root ourselves, yet to wander, to collapse inward, yet to radiate outward, to die, yet to echo forever. And the runaway pulsar, in particular, is the ultimate expression of this paradox. It is a star that could not stay home. It was born in a furnace, thrown across the night, and now races endlessly with no destination, only momentum and memory. Astronomers sometimes refer to them as orphaned remnants, yet that phrase fails to capture the grandeur of what they are. These are cosmic mariners, crossing space not in ships but as themselves, whole, compact, unyielding. They carry their birthmarks in their spin, their scars in their heat signatures, their history in their paths. And their stories are still being written, with each tick of their spinning bodies acting as a celestial clock, keeping time for a universe too vast to comprehend. So as you gaze up at the night sky and see the stars shining quietly above, remember, some of those lights are not where they once were. Some are fleeing. Some are already gone. And some, runaway pulsars, are still pulsing, still racing, still alive with the force of their own creation. In the silence between those pulses lies one of the greatest stories the universe has ever told. The trail of the runaway pulsar is more than just a cosmic curiosity. It's a signature, a scar across the fabric of the galaxy. It marks where something once lived, where it died, and how it refused to rest. Each runaway pulsar is like a comet that never burns out, a traveler flung into the darkness by titanic violence, and now bearing witness to regions of space no other known object has traversed with such defiance. And in that trail lies evidence, not only of the mechanisms that birthed it, but also of the unseen forces it encounters as it surges forward. These trails are sometimes visible. In some cases, they appear as bow shocks. Arc-shaped clouds of gas and plasma form the head of the pulsar's motion, similar to the wave that forms at the bow of a speeding boat. These bow shocks can glow in infrared or X-rays and offer a dramatic visual clue to the pulsar's supersonic journey through the interstellar medium. As the neutron star barrels through clouds of gas, its powerful magnetic field and relativistic wind plow into the material, creating a glowing crescent and a trailing tail. These structures aren't just beautiful, they're crucial. They reveal the direction of the pulsar's motion, its velocity, and even hints about the density and composition of the space it's crossing. One particularly famous example is the Guitar Nebula, shaped, quite strikingly, like a guitar. It was sculpted by a pulsar racing through space at over 1,000 kilometers per second. As its high-speed winds collided with surrounding material, they created the eerie, elongated shape that has fascinated astronomers for decades. That this bizarre, musical silhouette was carved not by hand, but by the dying breath of a collapsed star, speaks to the profound drama unfolding silently in the heavens above. Not every runaway pulsar leaves such dramatic traces. Some vanish into the darkness, detectable only by their tight, clock-like pulses. Others emit beams too narrow or faint for our telescopes to pick up, whispers drowned by cosmic noise. Still, we suspect their existence because of gravitational anomalies or because their trajectories align with known supernova remnants. These are the lost ones, the ghost runners of the galaxy. We may not see them directly, but we know they are out there. When astronomers track a pulsar's path backward, they often discover that it aligns neatly with the center of a supernova explosion. This gives credence to the theory that asymmetric supernovae, where one side of the star collapses more violently than the other, can impart a significant kick to the resulting neutron star. These kicks are incredibly efficient, transferring a huge amount of momentum in a fraction of a second. The result? A stellar core, just 20 kilometers across, shot out into the galaxy at hundreds, or even thousands of kilometers per second. What remains less understood, however, is why these kicks occur in some supernovae and not others. The physics of core collapse supernovae is still deeply mysterious, involving extreme temperatures, chaotic neutrino fluxes, and magnetic turbulence beyond our current ability to simulate. Perhaps there are magnetic fields so powerful they channel energy asymmetrically, or jet-like explosions that punch through the star's crust at odd angles. Or maybe the core's collapse is disrupted by instabilities that bias one direction over another. Each new runaway pulsar we discover gives us one more data point, one more clue to understanding the chaotic moments of stellar death. It is also worth pondering how many of these pulsars escape detection entirely. For every pulsar whose beam points toward Earth, there are many whose beams point elsewhere. Because pulsars emit in narrow cones, like lighthouse beams, we only detect them if we are lucky enough to stand in the path of that sweeping emission. A runaway pulsar could pass within a few light years of Earth, and remain entirely invisible if its beam misses us. This means the galaxy could be teeming with these silent travelers, rogue cores flying through the dark, unseen yet numerous. Some of these runaway pulsars may even be relics from an earlier age of the galaxy, neutron stars born in the early epochs of stellar evolution and kicked into the galactic halo long before our sun was even born. They may now drift in the sparsest regions of the Milky Way, their emissions faded, their rotations slowed, their energy spent. These ancient wanderers might carry within them clues to the chemical composition and stellar dynamics of a younger galaxy, a fossil record not in rock, but in magnetism, spin, and motion. And it gets stranger still. Some pulsars might not just be traveling alone, but as part of complex trajectories, dancing not just through empty space but in the gravitational grip of galactic structures we can't see. It's conceivable that some runaway pulsars are affected by dark matter subhalos, clumps of invisible mass theorized to populate the galaxy. If such a subhalo passed near a pulsar's path, it could subtly alter its trajectory, providing indirect evidence of dark matter's elusive presence. In this way, pulsars could become gravitational test particles, mapping the invisible architecture of the Milky Way. And consider this. A fast-moving pulsar with a sufficiently strong magnetic field may also produce gamma rays, high-energy photons born of particles accelerated to near-light speeds. These gamma ray emissions, detected by space telescopes like the Fermi Gamma Ray Space Telescope, are another way to trace runaway pulsars across vast distances. In some cases, the gamma ray glow extends far beyond the pulsar itself, revealing the pulsar wind nebula, a glowing cloud of relativistic particles pushed out by the pulsar's magnetic field. The shape and structure of this nebula can be twisted, stretched, or curved by the pulsar's velocity, telling a vivid story of its motion through space. As data accumulates, some researchers have even tried to classify runaway pulsars into distinct groups based on their velocities, emission types, and trail signatures. There may be fast movers with weak emissions, slow movers with strong gamma ray signatures, and outliers with unexplainable properties. It's like assembling a bestiary of stellar remnants, each one representing a different evolutionary path, a different death, a different story written in speed and magnetism. All the while, the core questions remain: how fast can a pulsar truly go? What is the absolute limit of a supernova kick? Could a pulsar be accelerated by other forces, gravitational slingshots, interactions with companion stars, even collision with other stellar remnants? Might some exotic event, such as a merger between a white dwarf and a neutron star, create a wholly new class of runaway object? As we expand our reach into the cosmos, through telescopes, space probes, and theoretical models, we begin to sense that runaway pulsars are not rare exceptions, but natural products of a dynamic, violent galaxy. They are not intruders, they are messengers. They do not flee, they voyage. Their motion is not chaos, it is the long echo of order disrupted and reformed. And we, watching from this small planet, try to decode those echoes, pulse by pulse, kilometer by kilometer, mystery by mystery. We've chased runaway pulsars across the Milky Way, followed the shockwaves of their violent births, traced their arcs through space, and listened to the rhythm of their electromagnetic heartbeats. But even now, our understanding feels partial, as if we're seeing only the silhouette of something far grander. Because what lies beneath the surface of these stellar remnants, what truly powers their behavior, is not just astrophysics, but the story of gravity's rawest extremes, of quantum mechanics pushed beyond its boundaries, and of time itself sculpted by density and speed. A runaway pulsar isn't just moving fast, it's dragging spacetime along with it. According to general relativity, any massive, spinning object warps the very fabric of the cosmos. In the case of a neutron star, especially one hurtling at hundreds or thousands of kilometers per second, this warping becomes more than academic. These objects don't simply curve spacetime, they twist it. This effect, known as frame dragging or the lens stirring effect, is typically tiny around planets like Earth, but around a pulsar, it can be significant, especially when coupled with the object's immense density and rapid motion. Theoretically, a runaway pulsar's path could subtly alter the timing of signals received from other distant cosmic sources, like gravitational clocks ticking through a distorted corridor. That brings us to pulsar timing arrays, global networks of radio telescopes that observe millisecond pulsars with extreme precision, looking for minute shifts in their pulses that could reveal the passage of gravitational waves. These waves, ripples in space-time predicted by Einstein, are emitted by cataclysmic cosmic events like black hole mergers. But runaway pulsars themselves, with their immense kinetic energy and dense mass, might also interact with gravitational wave backgrounds in ways we're only beginning to imagine. Their paths, when mapped precisely over decades, could act like needles moving through the invisible threads of gravitational energy, highlighting bends, compressions, or even anomalies in the cosmic tapestry. Consider, for instance, the possibility that a runaway pulsar, traveling near a dense cluster of dark matter, might experience unexplained deviations in its motion. We could track these discrepancies over time, comparing them to known models, and thereby test hypotheses about the structure of dark matter, whether it's smoothly distributed or clumpy, whether it interacts only gravitationally or has subtle self-interactions. In this way, runaway pulsars become not just relics of stellar death, but tools for probing the unseen universe. And it's not just their movement that fascinates us, it's their life after movement. Pulsars don't last forever. They spin down, losing energy to radiation and particle winds, eventually fading into what's called a dead neutron star. But in runaway pulsars, where high velocity might lead to rare encounters or interactions, this decay process could be altered. A high-speed neutron star plowing through a dense molecular cloud might be reignited, its surface superheated, its emissions temporarily boosted. Or it might collide with smaller celestial bodies, asteroids, rogue planets, or even another neutron star, triggering bursts or even mini gamma-ray flares. These scenarios are speculative, but not out of reach. Our instruments are improving. New observatories like the Square Kilometer Array, SKA, and future space-based X-ray and gamma-ray telescopes will soon be able to observe pulsars at distances and sensitivities never before possible. And when they do, we may finally catch the more elusive members of this runaway tribe, the faint ones, the tilted ones, the near-dead ones whispering in X-rays from the void. And then there's the chilling, beautiful question of whether runaway pulsars have already passed near us. It's not fantasy to think that tens of thousands, or even millions, of years ago, a neutron star may have screamed past our solar system. If close enough, its radiation could have subtly influenced Earth's atmosphere, triggered unusual aurorae, or even played a role in mass extinctions through increased cosmic ray flux. These are ideas currently being explored by astrobiologists and geophysicists who study isotopic anomalies in ancient rocks, such as increased levels of iron-60, an isotope linked to supernova debris. If a runaway pulsar was once the remnant of such a nearby explosion, it could now be traveling silently through the galaxy, long gone, never seen, but having left its fingerprint in our planet's fossil record. It is in such possibilities that the story of runaway pulsars transcends science and enters poetry. These objects are no longer just out there, they may be part of our story. Their paths, though distant, might intersect with ours in time and influence. Their pulses might carry, encoded within their rhythm, a shared history with Earth. And yet, for all we have discussed, we've barely scratched the surface. New simulations have proposed that some pulsars may achieve even more extreme velocities not from core collapse alone, but from rare multi-body interactions. In dense stellar clusters, where stars orbit in close quarters, binary systems can be disrupted by encounters with black holes. If a binary neutron star system is disrupted by a nearby black hole, one star might be flung outward at speeds exceeding 5,000 km per second, potentially the fastest stellar remnant ever observed. These scenarios are difficult to model, but their existence would help explain some of the more mysterious high-velocity pulsars observed today, whose energies seem too great to arise from conventional supernova kicks. In still rarer circumstances, a neutron star might pass through the accretion disk of a supermassive black hole, like Sagittarius A at the center of our galaxy. This encounter could accelerate it dramatically, or tear it apart, depending on proximity. If ejected, such a neutron star might emerge not only with increased velocity, but also with exotic properties, its magnetosphere disturbed, its rotation altered, its very crust cracked or melted. Such a star might appear anomalous to us, a weird pulsar whose behavior doesn't fit any model. Indeed, some of the pulsars we've already observed may be these galactic castaways. We see their strange emissions, odd periodicities, inconsistent glitches, and try to fit them into existing categories. But maybe they aren't strange, they're just survivors of rare, violent gravitational catapults. Each one a cosmic story, told in pulses, in speed, and in silence. The next generation of astrophysics will be shaped by these questions. We will not just look for runaway pulsars, we will learn from them. They will become our interstellar GPS, our gravitational wave detectors, our messengers from the past. And perhaps, as we map their journeys across the void, we'll better understand our own place in the cosmos, our velocity, our origins, our potential to one day, perhaps, become wanderers ourselves. Because runaway pulsars don't just remind us of destruction. They remind us of what remains after. Of the power to move forward through vast darkness. Of momentum born from chaos. Of persistence written in light. And if one of them, someday, crosses close enough for us to hear it clearly, maybe we'll realize that the stars themselves are not only watching us, but calling out, across eons, in voices forged from fire. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.